Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So my dear students, quickly just let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Welcome back everyone, welcome back. So give me some green signal from the chats so that I'll get to know I'm perfectly audible and visible to every one of you. Quickly, my dear students, in the chats. Quickly, let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to everyone. Yeah? Good evening all, good evening. Perfect. So my dear students, as you all must be knowing, in the last session, we completed the chemical equilibrium. And today, again, we are going to do one more important chapter of your chemistry, right? Majority of the students, majority of the NEET aspirants, they consider this chapter tough, ionic equilibrium. But again, the way we start every chapter with the basics, with the scratch, from the scratch itself, in the similar way, we'll be starting this particular chapter with the scratch, right? So imagine as if you have never studied this chapter before, right? So let's exactly get to know about ionic equilibrium in detail from the exact basics itself, right? So are you guys ready for it? Let me know once in the chats. Quickly, my dear students, are you ready for this ionic equilibrium? Yes or no in the chats. Quickly, my dear students. Well, the ones who are new to the channel, who do not know me, a quick introduction about me. And this is the introduction about me. You can go through it afterwards, right? At the end of the session. Well, the ones who have not liked the session yet, I would want every one of you to like this particular session. Do share this particular video with everyone. Whosoever is preparing for NEET 2024 or even 2025. This particular session is for every single guy. And my dear students, at the same time, if you have not subscribed to this channel yet, I would want every one of you to subscribe to the channel, right? And do share this particular channel with every single one. Whosoever is preparing for NEET 2024 or even 2025, right? So people, should we start the session? Let me know quickly in the chats. Should we start the session? Are you guys ready with your pen and paper? Are you guys ready with your pen and paper? Quickly, let me know first. Thank you, everyone. Thank you so much. So let me know in the chats with some fire symbols, yeah. Let's kickstart this particular chapter as well, and let's try to finish it off from the exact basics, yeah. Perfect, guys. So as I told you, I'll be starting this chapter from exact basics. So the first topic, the first and the basic topic with which I shall be starting this chapter, that is going to be electrolytes, right? You must have come across this term, electrolytes. Let's get to know what electrolytes exactly are all about. How do we classify these electrolytes? Because in this particular chapter, we have to deal only with the electrolytes. So let's get to know exactly what the electrolytes are all about. My dear students, it's very simple and basic. Try to understand the definition, then slowly we'll go towards the complex things as well. Yeah. So first of all, electrolytes are those substances which on dissolving in water dissociates into their ions. Electrolytes are basically those substances which on dissolving in water, they dissociate into their respective ions. Any such substance which on dissolving in water dissociates into its respective ions, we call that substance as the electrolyte. So what is electrolyte in short? It is that substance which on dissolving in water dissociates into its respective ions, right? Very simple and basic definition. Now, dear students, we classify these electrolytes basically into two types. One is strong electrolyte, one is weak electrolyte. Let's exactly get to know what strong electrolytes are and what weak electrolytes are. This is complete basics which I'm telling you. My dear students, strong electrolytes are those substances which are completely ionized, which are completely dissociated in their aqueous solution. Any such substance which dissociates completely into its respective ions, that's something which you call a strong electrolyte. For example, let's say you've got AB solid. Let's say you've got AB solid. Now you're introducing this AB solid into water, for example. I'm assuming that this AB solid, when introduced into water, let's assume that it got dissociated completely. It got 100% dissociated into its ions. So I'll be calling this particular electrolyte over here as strong electrolyte. So what is a strong electrolyte? That substance which undergoes 100% dissociation on dissolving in water, right? At the same time, if you ask me, what about degree of dissociation? What about degree of ionization for these strong electrolytes? You'll say the degree of ionization for the strong electrolytes, it's always equal to 1, right? It's always equal to 1 because the electrolyte, it gets completely dissociated into its ions. If you remember in the chemical equilibrium, we used to call this alpha as degree of dissociation. But in this particular chapter, I'll be calling this alpha as degree of ionization. It is just the terminologies are different, but the meaning is actually same. Terminologies are different, but the meaning is same. In chemical equilibrium, we used to call it as degree of dissociation, and here I'll be calling it as degree of ionization, right? Rest, every single thing is same. Perfect. If you remember, I told you one more thing. I told you percentage dissociation. Here I'll be writing percentage ionization. Percentage ionization is equal to degree of ionization multiplied by 100, right? Now, I'm telling you a strong electrolyte, it gets 100% ionized. That means percentage ionization of the strong electrolyte is 100, which is equal to alpha multiplied by 100, right? So the value of alpha is coming out to be directly 1. As I told you, in case of strong electrolytes, the degree of ionization is always equal to 1, right? Again, simple and basic. Now, my dear students, you must be thinking, what are the examples of these strong electrolytes? My dear students, all the strong acids, all the strong bases, and all the water-soluble salts, they are the examples of the strong electrolyte. So whenever you see a strong acid, whenever you see a strong base, whenever you see a water-soluble salt, when you introduce them into water, they'll get 100% ionized. They'll get 100% dissociated into their ions. And any such substance which gets 100% dissociated into its ions, we call that as the strong electrolyte. So do remember, all your strong acids, all your strong bases, and all your water-soluble salts, these are the examples of the strong electrolytes. Whose alpha, degree of ionization, that's equal to 1, right? At the same time, let me tell you, the general salts of alkali metals. General salts of alkali metals. For example, alkali metals, all of you must be familiar with, right? Lithium, sodium, potassium, rubidium, cesium. When you take any salt of these alkali metals, for example, you're taking the salt NaCl. It is the salt of alkali metal, right? It's the salt of alkali metal. So all the salts of alkali metals, even all the salts of NH4 positive. For example, you have got NH4Cl as the salt. Should I be calling this salt as the salt of NH4 positive? Absolutely, this is the salt of NH4 positive. And all the salts of NO3 negative, right? For example, you have got NH4NO3, NH4NO3. For example, you have got KNO3. Perfect. So these are what I'll be calling as the salts of NO3 negatives. Let me tell you, all the salts of alkali metals, all the salts of NH4 positive ions, all the salts of NO3 negative ions, these are considered to be water-soluble salts, and water-soluble salts are always the examples of what? These are always the examples of strong electrolytes. So these are some basic things which I would want all of you to remember. Any such substance which gets 100% ionized, which gets 100% dissociated on dissolving in water. That's something which I'll be calling a strong electrolyte. All the strong acids, all the strong bases, all the water-soluble salts, these are the examples of the strong electrolytes, right? General salts of alkali metals, general salts of NH4 positive, general salts of NO3 negative. These are all the examples of the water-soluble salts, and you know, water-soluble salts are the examples of the strong electrolytes. So I hope you guys are going to remember this from now onwards. My dear students, what about weak electrolytes? Weak electrolytes, they are not 100% dissociated on dissolving in water, right? I would say they are partially ionized. When you put a weak electrolyte in water, it does not get 100% ionized. It does not get 100% dissociated upon dissolving in water. It is partially ionized in its aqueous solution. Now you must be thinking, if it is partially ionized, its alpha value. Its alpha value. Will it be equal to 1? No. It will be greater than 0 and less than 1. It will be greater than 0 and less than 1. Right? And at the same time, you must be thinking, what are the examples of these weak electrolytes? My dear students, all the weak acids, all the weak bases, all the weak acids, all the weak bases, they are examples of weak electrolytes. All the weak acids, all the weak bases, they are the examples of the weak electrolytes which do not get completely ionized when we introduce them into water. What are the other examples of weak electrolytes? All the sparingly soluble salts. What are sparingly soluble salts? You'll get to know in this chapter only, but afterwards, right? All the sparingly soluble salts, these are the examples of weak electrolytes, and these are the examples of your sparingly soluble salts, right? Which are again considered to be weak electrolytes. So few things which I would want you to remember. Any substance which do not get 100% ionized in their aqueous solution, you call that as weak electrolyte. Weak acids, weak bases, sparingly soluble salts, these are all examples of weak electrolytes, right? These are all examples of weak electrolytes which do not get 100% dissociated into their ions. And these are some examples of the weak electrolytes, right? My dear students, there is one important point which I would want to mention here, right? Which I'll be using everywhere in ionic equilibrium. Let me tell you, all the weak electrolytes are considered to be, just a second. See, I'm writing a weak electrolyte. A weak electrolyte will be always in equilibrium with its ions. In this complete chapter, this is a particular statement will be following throughout. Whenever you see a weak electrolyte, weak electrolyte will be always in equilibrium with its ions. For example, if I take a weak acid, CH3COH, right? This is a weak acid, acidic acid. It's an example of weak acid. Since it's a weak electrolyte, so it's going to remain in equilibrium with its ions, and its ions are going to be CH3CO negative aqueous plus H positive aqueous, right? For example, you have got NH4OH. This is a weak base. It's a weak base. When you put it into water, right, it gets dissociated into its ions, and its ions are NH4 positive aqueous plus OH negative aqueous. Now what I'm telling you is, I'm telling you this NH4OH, it's a weak base. If it is a weak base, it's going to remain in equilibrium with its ions. So in short, whenever you see a weak electrolyte, you'll be always considering that the weak electrolyte is in equilibrium with its ions. This is one important point which I would want you guys to remember from now on, right? Strong electrolyte, it gets completely ionized. It is not going to remain in equilibrium with its ions. Whereas when I'll be talking about the weak electrolyte, in its aqueous solution, do remember, it will be always in equilibrium with its ions. I hope this is super clear to everyone, right? So this was just the basics, right? Now we are going to understand the actual stuff over here. Now we are going to enter into the chapter. Till now, whatever I was telling you till now, that was complete basics, right? Now, my dear students, we are going to enter into the chapter. Now it is the time to start the chapter. Okay? So the first topic which we have to discuss here, that is ionization constant of a weak electrolyte. Ionization constant of a weak electrolyte. Try to understand what I'm going to say. My dear students, for example, I have got a weak electrolyte AB. Let's say AB is a weak electrolyte. You are going to introduce it into water. Since it's a weak electrolyte, so it is going to remain in equilibrium with its ions, and its ions are going to be A positive aqueous plus B negative aqueous, right? It's going to be A positive aqueous plus B negative aqueous. Now, my dear students, let's assume the degree of ionization of this weak electrolyte. Let's assume that is alpha. And at the same time, let's assume initially at time t is equal to 0, the concentration of this weak electrolyte is C, for example. It is C molar, the concentration of weak electrolyte. So initially, the concentration of weak electrolyte is C. Time t is equal to 0 means that the dissociation has not started yet. If the dissociation has not started yet, I must say the container in which this reaction will be taking place, in that container, the concentration of A positive and B negative initially will be 0 because the dissociation has not started yet. AB has not got dissociated into ions yet, right? So concentration of A positive and B negative at time t is equal to 0 will be absolutely 0, right? Now, my dear students, at equilibrium, when equilibrium is established in the reaction, when equilibrium is established in the reaction, if I ask you, what is the concentration of reactant left in the container? You will be using the same procedure as we used to do in chemical equilibrium. You are going to treat this concentration in the similar way as you used to treat moles. Do you remember in equilibrium, chemical equilibrium, it used to be A00, 0. Then it used to be A minus A alpha. This used to be A alpha. This used to be A alpha. So the way we used to treat the moles, in the similar way, you guys are going to treat the concentration as well. Now try to understand. The initial concentration of AB was C. Now from C, how much will get dissociated? From C, C alpha will get dissociated. So how much will be left? C minus C alpha will be left. As simple as that. Now 1 mole of AB gives 1 mole of A positive. From C alpha, you get C alpha exactly. 1 mole of AB gives 1 mole of B negative. From C alpha, you exactly get C alpha. So what did I calculate? Try to understand these things. What are these things exactly? These are the concentrations of reactants and products present in the container at equilibrium. When equilibrium got established in the reaction, I got the concentration of each reactant and product at equilibrium. Correct? Now, my dear students, the way we used to write Kc, do you remember how we used to write the expression for Kc? Well, let me tell you, in ionic equilibrium, Kc is represented by Ki. Kc is represented by Ki. That's all. What this Ki is called? Ki is something which you call as ionization constant. It is something which you call as ionization constant of what? Of a weak electrolyte. Of a weak electrolyte. Which weak electrolyte? AB. Perfect. The way you used to write the expression for Kc, in the similar way, you guys are going to write the expression for Ki. You'll be starting from the product. Concentration of A positive at equilibrium raised power stoichiometric coefficient. Concentration of B negative at equilibrium raised power stoichiometric coefficient divided by concentration of AB at equilibrium raised power stoichiometric coefficient. As simple as that. Now try to understand few important things. Try to understand few important things. I'm teaching you the complete basics. If this is clear, then only the chapter will get clear to you. Now, my dear students, try to write the Ki expression in detail. Ki is equal to concentration of A positive at equilibrium, C alpha. Concentration of B negative at equilibrium, C alpha. So C alpha and C alpha makes it C square alpha square divided by concentration of AB at equilibrium, that is C minus C alpha, right? So it is C minus C alpha. So my dear students, just write it like this. It is C square alpha square, take C common, it's going to be 1 minus alpha in the denominator. So 1 of C and 1 of C gets cancelled out. So Ki comes out to be equal to C alpha square divided by 1 minus alpha. So first of all, this is how you write the expression for the ionization constant of a weak electrolyte which undergoes the dissociation 1:1:1, right? Which undergoes the dissociation under the stoichiometry 1:1:1, right? I hope this is clear. Now, my dear students, after reaching till here, we'll be assuming certain things. Try to understand what I'm going to say. Till now, we got the Ki value, which is C alpha square divided by 1 minus. After reaching here, what we shall be doing, we shall be assuming certain things. I shall be assuming let alpha value is less than 0.05. I'm assuming that alpha is less than 0.05. I'm assuming that the percentage ionization of this electrolyte, at equilibrium, that is less than 50%. I'm assuming less than 50, sorry, that is less than 5%. I'm assuming less than 5% of electrolyte got dissociated when equilibrium was established. I'm assuming when 5% of electrolyte got dissociated, at that point of time only equilibrium is established. For example, I'm assuming that when 5% reaction was completed, at that point of time equilibrium is established. So what I'm assuming is, if I'm saying let alpha is less than 0.05, that means less than 5% reactant has got converted into product at equilibrium, right? As simple as that. So let alpha is less than 0.05. My dear students, if you assume that alpha is less than 0.05, at that point of time, you can neglect alpha in comparison to 1. And when you neglect alpha in comparison to 1, you can write Ki as C alpha square, and you can get the value of alpha from here. Just remember this procedure. You'll get its exact idea in some time when I'll be solving the questions. So first of all, you need to get the value of alpha. Let me tell you, this Ki will be given to us, T will be given to us. Can't we calculate alpha from there? Absolutely, we'll be calculating alpha from here. Absolutely, we shall be calculating alpha from here. I'm assuming less than 5% of reaction got completed. When less than 5% of reaction got completed, equilibrium got established. I'm assuming the degree of ionization of this weak electrolyte is less than 0.05. Right? So my dear students, when I let alpha be less than 0.05, so 1 minus alpha will be taken as 1. So Ki will be taken as C alpha square. Alpha will be taken as under root of Ki by C. And let me tell you, Ki value will be given to us as per the equation. C value will be given to us as per the equation. We just have to put the values. After putting the values, we'll be getting the value of alpha. We will be getting the value of alpha. And if the alpha value, after putting the terms in this equation, if the value of alpha actually comes out to be less than 0.05, that means whatever assumption we have done, that's absolutely correct. That's absolutely correct. If alpha does not come out to be less than 0.05, after solving this equation, if alpha does not come out to be less than 0.05, that means our assumption is absolutely wrong. You'll be getting its clear-cut idea in some time. But I hope my point here was to let you know how to write the ionization constant expression. If this ionization constant expression is clear, then I'm going to do one question based on the same so that you'll get the idea of what exactly I was talking about till now. Try to understand what I'm saying. Calculate the concentration of each ion at equilibrium for 0.1 molar solution of a weak electrolyte AB. So as per the question, you are given with a weak electrolyte AB. If it is a weak electrolyte, it's going to remain in equilibrium with its ions. Its ions are A positive aqueous plus B negative aqueous. Absolutely correct. Yeah. Now, dear students, at time t is equal to 0, let the concentration of AB aqueous is C, right? And this concentration of AB aqueous is given to me as 0.1 molar as per the equation. So initially, when the reaction has not started, this will be 0, this will be 0. Now you tell me at equilibrium, what is the concentration of reactant left? Let's assume the degree of ionization is alpha. So it is supposed to be C minus C alpha. 1 mole of AB gives 1 mole of A positive. So from C alpha, you get C alpha. From C alpha, you get C alpha, right? Now, my dear students, if I write the expression for Ki expression, ionization constant of weak electrolyte, Ki, how exactly you are going to write it? Concentration of A positive at equilibrium multiplied by concentration of B negative at equilibrium divided by concentration of AB, which I told you a few minutes back only, that is C alpha square divided by 1 minus alpha. Correct till here? I hope every single thing is clear till here, right? Now, dear students, these are basically two questions. In the first question, we have to assume that ionization constant is equal to 10 raised to minus 5. In the first question, it's mentioned that ionization constant is equal to 10 raised to minus 5. Okay. Till here, everything is done. After this, I told you to follow certain assumptions. What I'll be doing after this? I'll be assuming let alpha value is less than 0.05. If alpha is less than 0.05, at that point of time, I can say 1 minus alpha is equal to 1. And if 1 minus alpha is equal to 1, that means I can say ki is nothing, that is c alpha square. And from here, you'll be getting the value of alpha, which is under root of ki divided by c. Now you tell me, what is the value of ki? That's 10 raised power minus 5. What is the value of c? 10 raised power minus 1. So it comes out to be 10 raised power minus 4. Its root is 0.01. Now, my dear students, try to analyze the things. Whatever alpha value you have calculated from here, is the alpha actually coming out to be less than 0.05 or not? Absolutely, the value of alpha is coming out to be less than 0.05. That means whatever assumption you have done over here, the assumption is all perfect. Right? So you got the value of alpha. If you got the value of alpha, what was I supposed to calculate? Calculate the concentration of each ion at equilibrium. Now you tell me, concentration of each ion at equilibrium. Concentration of A positive and B negative at equilibrium. I'll say concentration of A positive at equilibrium is equal to the concentration of B negative at equilibrium, and both the values exactly are equal to C times alpha. Now people, are you given with the C value? Absolutely, you're given with the C value. That is 0.1 molar, which is 10 raised power minus 1. Alpha value, which is 10 raised power minus 2. So the value comes out to be 10 raised power minus 3 molar. So this is the concentration of A positive as well as B negative when equilibrium is established in the reaction. Is this point clear to every single guy? Say yes or no in the charts quickly. Say yes or no in the charts quickly, my dear students. Everyone, quickly. So the first part of the question is done and dusted. Right? The first part of the question is done and dusted. Perfect. Now, my dear students, since the first part of the question is done, let's try to do the second part of the question. In the second part of the question, we have to assume that the ionization constant of the weak electrolyte is 10 raised power minus 2. Now, let's see what change will occur over here. See, guys, the second part of the question. You have got an electrolyte AB aqueous. Right? Since it's a weak electrolyte, so it's going to remain in equilibrium with its ions, and its ions are A positive aqueous and B negative aqueous. I think all the procedure you already know. At time t is equal to 0, the concentration of this one is 0.1 molar. So this has to be 0, this has to be 0. Degree of ionization is alpha. So at equilibrium, what will be the concentration of AB aqueous? It is C minus C alpha. Sorry. So this is going to be C alpha and this is going to be C alpha, right? Now, as per the question, we have to consider the Ki value, ionization constant value, as 10 raised power minus 2. So it is 10 raised power minus 2, correct? Perfect. Now, my dear students, I would want you guys to write the Ki expression. Ki expression you already know, concentration of A positive, concentration of B negative, divided by concentration of AB. So final expression will be C alpha square divided by 1 minus. Now, again, the same thing. Let alpha value is less than 0.05. At that point of time, instead of 1 minus alpha, I can write 1. Therefore, Ki value will be just equal to C alpha square, and alpha will be equal to under root of Ki divided by C. Yeah? Right? Now, people, alpha is equal to under root of Ki by C. Now, you tell me, alpha is equal to under root of, what is Ki? 10 raised power minus 2. What is C? C is 0.1 molar. That means 10 raised power minus 1. Correct? That means 10 raised power minus 1. Which is going to be equal to under root of 10 raised power minus 1. Under root of 10 raised power minus 1 is 1 divided by root 10. 1 by root 10 is approximately 3 point something. Right? And approximate value will be 0.3. This is the approximate value of what? This is the approximate value of alpha. I had assumed that alpha value is less than 0.05. But have a look. Is alpha coming out to be less than 0.05? Alpha is not coming out to be less than 0.05. That means whatever assumption we have done over here, you cannot assume it. This is wrong. You cannot neglect alpha in comparison to 1. If you cannot neglect alpha in comparison to 1, that means how you are going to calculate Ki. In the Ki expression, you have to keep all the terms. C alpha square divided by 1 minus alpha. You cannot neglect alpha now. You cannot neglect alpha at this point of time because alpha is not coming out to be less than 0.05. Yeah. What are we supposed to calculate? We are supposed to calculate the concentration of A positive and concentration of B negative at equilibrium, correct? Now, how we are going to solve it? Now, have a look. Now, we got to know that this is the actual Ki expression. You cannot neglect alpha. So, what you'll be doing? Put the value of Ki in this expression, which is 10 raised power minus 2. And 10 raised power minus 2, you can write it like this. You can write it as 1 divided by 10 raised power 2 is equal to C. C is the concentration of this electrolyte. 10 raised power minus 1. 10 raised power minus 1 can be written as 1 by 10 alpha square multiplied by 1 minus alpha. So 10 and 10 got cancelled. So over here, if you have a look exactly what you'll be getting. You'll be getting 10 alpha square. 10 alpha square is equal to 1 minus alpha. So it's going to be 10 alpha square is equal to 1 minus alpha, or you can say 10 alpha square plus alpha minus 1 is equal to 0. So do you see over here one quadratic equation got developed? You got a quadratic equation, my dear student. You got a quadratic equation. Now you know exactly how to solve the quadratic equation. Alpha is equal to minus b plus minus root of b square minus 4ac divided by 2a. So after solving this quadratic, can't you get the value of alpha? Exactly, you'll be getting the value of alpha. And the value of alpha, which you'll be getting from here, just put the value of alpha here. C value, you know, alpha you'll be calculating. So C alpha will give you the concentration of A positive at equilibrium. Similarly, C alpha will give you the concentration of B negative at equilibrium, right? I hope you understood both the scenarios. When to neglect alpha and when not to neglect alpha. Say yes or no in the chats quickly. Say yes or no in the chats quickly, my dear students. Every one of you. Every one of you. This is the most important point here. This is the most important point here. To understand when to neglect alpha and when not. I hope this is super clear, yeah? All right. Now let's have a look. Look at this particular topic. Topic by topic, we'll be doing the questions. And I'm 100% sure you'll find this ionic equilibrium very, very, very easy. My dear students, till your NEET level, when it comes to NEET level or JEE mains level, this chapter is considered to be easy only, provided you know the basics. But from the advanced point of view, this chapter is considered to be tough. Yeah? But for your level or mains level, this is damn easy, provided you know the basics of it. Right? So we'll be studying a topic followed by question, topic followed by question, so that you get to know the application of the concept as well. Yeah? Now guys, few minutes back, I told you, all the weak acids, all the weak bases, they are the examples of weak electrolytes. For example, the weak electrolyte, which I am going to take into consideration, let's assume that is weak acid. Let's assume that is weak acid. Let's say I've got a weak acid HA over here. It's a weak acid. If it's a weak acid, it's going to be considered as a weak electrolyte and it's going to remain in equilibrium with its ions. And its ions are H positive aqueous plus A negative aqueous. Right? Now the same procedure. Let's assume the degree of ionization of this weak acid is alpha. So at time t is equal to 0. Its concentration is C. This is 0. This is 0. At equilibrium, this is going to be C minus C alpha. This is going to be C alpha. This is going to be C alpha. Right? Now, how do we write the ionization constant of the weak electrolyte? It is represented by Ki. But when your weak electrolyte is weak acid, when your weak electrolyte is weak acid, you are not going to write Ki. Instead of Ki, you will be writing Ka. And what is this Ka called as? It is called as ionization constant of a weak acid. Basically, this ionization constant of weak acid, what is it? It is ionization constant of weak electrolyte only. It is just the terminologies are different. Meaning is same. If your weak electrolyte is weak acid, then instead of Ki, you will be writing Ka. Rest everything is same. It is going to be equal to concentration of H positive at equilibrium raised power stoichiometric coefficient, concentration of A negative at equilibrium raised power stoichiometric coefficient, concentration of HA at equilibrium raised power stoichiometric coefficient, which will finally again come out to be C alpha square divided by 1 minus alpha. And after this, I'm damn sure you exactly know what to do. What do we do after this? Assumption. Let alpha value be less than 0.05. Let alpha value be less than 0.05. Then get the value of alpha. If the alpha value comes out to be less than 0.05, that means your assumption is correct. If not, then you have to solve the quadratic equation to get the actual value of alpha. Similarly, my dear students, if your weak electrolyte is your weak base, let's say you're taking a weak base, BOH. It's a weak base. If it's a weak base, it's a weak electrolyte. If it's a weak electrolyte, it's going to remain in equilibrium with its ions. Its ions are B positive aqueous plus OH negative aqueous. Right? Now you know each and everything. At time t is equal to 0, this is C. This is 0, this is 0. Degree of ionization, that's alpha. So this has to be C minus C alpha. This has to be C alpha. This has to be C alpha. Now, dear students, particularly when your weak electrolyte is a weak base, at that point of time, Ki is replaced by the term Kb. Kb is something which I'll be calling as ionization constant of a weak base. Ionization constant of a weak base. How do I write this expression? You know how to write the expression. The same way as you used to write the expression for Kc, right? Concentration of B positive at equilibrium raised for stoichiometric coefficient. Concentration of OH negative at equilibrium raised for stoichiometric coefficient. Divided by concentration of BOH. As simple as that. So finally it comes out to be C alpha square divided by 1 minus alpha. And after this, you exactly know what to do. So from now onwards, try to remember one thing directly. If the electrolyte undergoes dissociation under the stoichiometry 1:1:1, its Ki will be always C alpha square divided by 1 minus alpha. If the electrolyte follows the dissociation under the category 1:1:1 stoichiometry, its Ki value will be always C alpha square divided by 1 minus alpha. Perfect. But if you change the stoichiometry, for example, this was 2 times. Let's say it was 2 times H positive. Here it will be 2 times C alpha. Here you have to introduce 2 as well. Perfect. I hope that thing is something which you already know. Yeah. Now, people, try to understand few important things. Try to understand few important things. If, for example, alpha value is less than 0.05, at that point of time, your alpha will come out to be, if alpha is less than 0.05, then 1 minus alpha can be written as 1, and alpha you'll be getting as Ka divided by C. And over here, alpha you'll be getting as under root of Kb divided by C. Correct? Now, my dear students, try to understand one simple conclusion. Alpha and Ka directly or inversely proportional. They are directly proportional. So more the value of Ka for an acid, more the value of ionization constant of an acid, I'll say more will be the value of alpha. More will be the value of alpha. More the value of alpha means more the percentage of acid, that got dissociated. And more acid getting dissociated means more will be the H positive concentration in the solution. More the H positive concentration in the solution, lesser is going to be the pH. Right? Lesser is going to be the pH. Are you relating all these things? More the value of Ka means more is the value of alpha. More value of alpha. That means more is the dissociation, more is the ionization, more the H positive concentration in, and lesser is going to be the pH. Right? Or you can say stronger is going to be the acid. Simple. Right? Look at this particular scenario. Alpha and Kb, they are again directly proportional. So more the value of alpha. More the value of Kb. If Kb value for the weak base is more, that means alpha value is more. If alpha for the weak base is more, that means this weak base has got dissociated more into its ions. So in the container, more will be the OH negative concentration, and more the OH negative concentration means more the basic strength. More the basic strength. More the basic strength means more is going to be the pH. More is going to be the pH. Right? Over here you can say more will be the acidic strength, right? Lesser the pH means more the acidic strength. All these things you already use in organic chemistry, right? I hope all these things are clear to you. So say yes or no in the chats if every single thing seems clear till here. And my dear students, if all these things are clear, let's try to solve certain questions. Weak acid, this is Ka, this is alpha. When you assume alpha is less than 0.05. This is alpha. When you assume alpha is less than 0.05. Perfect. And you got to know more Ka, Kb means more acidic basic strength for the same concentration. Yeah. Let's try to solve few questions so that you can completely analyze the things. See, learn the concept and try to utilize it in the question. That's how you actually learn the things, right? And if you learn together a lot of questions, if you learn together a lot of concepts and at the end you'll be solving the questions, it won't make a difference. You are not going to learn in a better way then. One concept, one question, one concept, one question. That has to be the strategy always, right? That's how you remember the approach to solve the questions as well. Okay, keep this thing in mind as well. All right, calculate the H positive concentration of a 0.05 molar CH3COH. Now, if I talk about CH3COH, acetic acid, it's a weak acid. Weak acid, weak electrolyte. Weak electrolyte remains in equilibrium with its ions. Its ions are CH3CO negative aqueous plus H positive aqueous. Agreed? Absolutely agreed. Yeah. Now, at time t is equal to 0, its concentration is C. This is 0. This is 0. Degree of ionization is alpha. At equilibrium, this has to be C minus C alpha. This has to be C alpha. This has to be C alpha. Now write the expression for Ka. That has to be equal to C alpha square divided by 1 minus alpha. Yeah. Now let's assume that alpha value is less than 0.05. At that point of time, instead of 1 minus alpha, you can write 1. Right? And eventually, Ka comes out to be equal to C alpha square. Therefore, alpha value will be equal to under root of Ka divided by C. Yes? Agree till here? Now, my dear students, tell me the value of Ka. Ka value as per the question, that's 1.25 into 10 raised power minus 6. What about the C value? C is the concentration of the weak acid, and concentration of weak acid is given to me as 0.05 molar. So this is 0.05. So this is 1, this is 25 times. So this is root of 25 into 10 raised power minus 6, which comes out to be 5 into 10 raised power minus 3. 5 into 10 raised power minus 3 means 0.005. Alpha value is coming out to be 0.005, which is actually less than 0.05, which is actually less than what I had assumed. I had assumed the alpha to be less than 0.05, which is coming out to be actually 0.005. So whatever assumption we have done, absolutely correct. So we got the value of alpha, that is 0.005, or you can say 5 into 10 raised power minus 3. So alpha we calculated. What are we actually supposed to calculate? The concentration of H positive. Tell me the concentration of H positive in the container at equilibrium. Finally, what is the concentration of H positive in the container? That's C alpha. So this is C multiplied by alpha. What is C value? That is 0.05. 0.05, which means 5 into 10 raised power minus 2. What about alpha? Alpha is 5 into 10 raised power minus 3. Alpha is 5 into 10 raised power minus 3. So the value comes out to be 25 into 10 raised power minus 5 molar. This is the concentration of H positive in the container, which we were supposed to calculate. Is this clear to everyone? Say yes or no in the chats quickly. Everyone, people. Everyone means everyone. Quickly. I hope it's absolutely clear. Try to understand one more question. One more question which will make this concept a little more stronger. Have a look. Calculate the ionization constant of a weak base. So as per the question, we have taken a weak base, NH4OH. If it is a weak base, it's going to remain in equilibrium with its ions. Its ions are NH4 positive aqueous plus OH negative aqueous. That's how it would have got dissociated. Now, all the things you already know. Initially at time t is equal to 0, the concentration of NH4OH is C, right? And how much it is? How much it is? 0.1 molar. This is 0, this is 0. Let's assume the degree of ionization is alpha. So at equilibrium, I must say the concentration of this NH4OH left in the container is C minus C alpha. So this is going to be C times alpha. Even this is going to be C times alpha. Right? Clear till here? Now, my dear students, if I ask you to write the expression for Kb, since it's a weak base, so ionization constant of a weak base, it undergoes the dissociation. It undergoes dissociation under the stoichiometry 1:1:1. So it directly has to be C alpha square divided by 1 minus alpha. Don't need to do lot. Now tell me one thing. Tell me one thing. It is mentioned in the question that the concentration of OH negative in the 0.1 molar aqueous solution is 0.05 molar. So concentration of OH negative in the aqueous solution at the end, that means concentration of OH negative at equilibrium, that's basically given to me as 0.05 molar. Now if I ask you what is the concentration of OH negative at equilibrium, that is, you'll say that is C alpha. So C alpha is equal to basically 0.05. Can I say alpha is nothing? That is 0.05 divided by C, and C is 0.1. The value will be 0.5. Alpha is coming out to be 0.5. Alpha is coming out to be 0.5. Now you tell me, if alpha is coming out to be 0.5, that means instead of 1 minus alpha, can you write 1? You cannot do that. Alpha value, it did not come out to be less than 0.05. So you cannot do the neglection. So this is the expression which you have to write now. You cannot neglect alpha here. You have to take this alpha in the denominator as well, right? So what are we supposed to calculate? We were supposed to calculate the ionization constant of the weak base. So Kb we were supposed to calculate. C value is 0.1. 10 raised power minus 1. Alpha square. Alpha is 0.5. 0.5 ka square divided by 1 minus 0.5. So 1 minus 0.5 is 0.5, 0.5, 0.5 cancel. So it comes out to be 0.05. So this is the value of ionization constant of the weak base which we were supposed to calculate. So let me know in the chats if every single thing is clear to you. Quickly guys. Quickly in the chats. Quickly in the chats. Yes? Perfect, guys. Now, there is one more important concept which is used in the entire equilibrium. That is common ion effect. One of the most important concepts, right? Let's try to understand what this concept exactly is and where do we exactly utilize this concept. Let's get to know one by one, right? Let's try to read its definition first. The separation of degree of ionization of a weak electrolyte when a strong electrolyte containing a common ion is added to it. I'm damn sure you did not get it, right? So let's try to understand it. See guys, for example, you have got a weak electrolyte. Let's say I'm taking weak acid. This is the weak acid which we have. This is the weak acid. That means we have got a weak electrolyte. If we have got a weak electrolyte, that means it's going to remain in equilibrium with its ions. Its ions are CH3CO negative aqueous plus H positive aqueous. Perfect. So I've taken a container in which CH3COH is in equilibrium with its ions. Agreed? Let's assume its degree of ionization is alpha. So initially at time t is equal to 0. This is C. This has to be 0. This has to be 0. Now when equilibrium is established in the reaction, so this has to be C minus C alpha. This is going to be C alpha. This is going to be C alpha. Right? Now dear students, try to understand one thing. I've taken a container. In which this weak electrolyte is in equilibrium with its ions. Now, in the same container, I am going to introduce a strong electrolyte. In the same container, I'm going to introduce a strong electrolyte. Right? Strong electrolyte HCl, I'm going to introduce in the same container. So it's going to get dissociated completely into its ions. It's going to get dissociated completely into its ions. Right? Now, let's assume that its initial concentration was C1, this was 0, this was 0. Now it's going to get completely dissociated into its ions. So its concentration will be 0 at the end. 1 mole gives 1 mole, C1 gives C1, this is C1. Now my dear students, try to understand one simple thing. I had a weak electrolyte in the container, which was in equilibrium with its ions. In the same container, I introduced a strong electrolyte. But you'll be introducing such a strong electrolyte which will be satisfying one condition. And the condition is that there should be one ion common in both. Is there any ion common in both? H positive, H positive. So you are going to add such a strong electrolyte which will satisfy the condition that one of the ion should be common in both, right? So whenever you see such kind of the thing, you have got a weak electrolyte, you are introducing a strong electrolyte into it, having a common ion. Now do remember at that point of time, common ion effect is going to operate. Now what this common ion effect does? What this common ion effect does? Before telling you that, tell me one thing. If I ask you, what is the total concentration of the common ion? Common ion is H positive. Concentration of H positive coming from this acid is C alpha. Concentration of H positive coming from this acid is C1. So total H positive concentration is C1 plus C alpha. C1 plus C alpha, right? Initially, if you try to observe one thing, initially, there was only weak acid in the container, which was in equilibrium with its ions. Now you are introducing a strong acid, right? By the introduction of strong acid, can I say you are increasing the H positive concentration in the container? Absolutely, you are increasing the H positive concentration. Now, you are increasing the H positive concentration in the container. Since this reaction was in equilibrium, now you are adding a strong acid. Due to the addition of strong acid, you are increasing the concentration of H positive. Which effect is going to operate? Le-Chatelet principle, you are going to operate. Whatever you do to a reaction at equilibrium exactly does opposite of what you do. I am trying to increase the H positive concentration by the addition of strong acid. Now equilibrium will try to decrease it. How equilibrium is going to decrease it? It will make sure the reaction shifts in the backward direction. And when this particular reaction shifts in the backward direction, that means the value of alpha for this weak electrolyte, is it increasing or decreasing? I must say the value of alpha for the weak electrolyte will be decreasing. Right? So my dear students, this decrease in the value of alpha, the suppression in the degree of ionization, the decrease in the degree of ionization when a strong electrolyte is added to a weak electrolyte having a common ion in between. This effect is what you call as common ion effect. This effect is what you call as common ion effect. The suppression, the decrease in the value of degree of ionization of a weak electrolyte when a strong electrolyte having a common ion is added to it. Right? For example, this particular alpha, when there was only weak electrolyte present in the container, which was in equilibrium with the ions. Let's assume that alpha was already less than 0.05. Now, by the addition of this strong acid, the alpha value would have further suppressed. The alpha value would have got further suppressed. So, wherever you see alpha, you can neglect the alpha. So, if I ask you the total H positive concentration, which is C1 plus C alpha, instead of this whole, you are only going to write C1. Because alpha has further suppressed, it has further decreased. Already it was less than 0.05. Now it has further decreased. Yeah? Right? Right, people? Now, I'm going to ask you one thing. Write the expression of Ka for this weak acid. It's going to be concentration of CH3CO negative, which is C alpha. Concentration of H positive at equilibrium, which is just C1, divided by concentration of CH3COH, which is C minus C alpha, take C common, state 1 minus alpha, so C cancel. So Ka value will be equal to C1 alpha divided by 1 minus alpha. Already, due to the addition of strong acid, alpha value has further suppressed. So wherever you want to neglect alpha, you can do that. So instead of 1 minus alpha, you can write 1. So from here, you can say Ka is equal to C1 alpha, or alpha value you got to know as Ka divided by C1. Ka divided by C1. Tell me, is this the old alpha or new alpha? Is this the alpha before the addition of strong electrolyte, or this is the alpha after the addition of strong electrolyte? Tell me, is this the alpha before operation of common ion or after operation of common ion? This is the value of alpha after the operation of common ion. Before the operation of common ion, when there was only weak acid in equilibrium with its ions, alpha at that point of time would have been under root of Ka by C. But now, it is going to be Ka divided by C1. Ka is the ionization constant of the weak acid. And what is C1? C1 is basically the concentration of common ion. The concentration of common ion coming from the strong electrolyte. Concentration of common ion coming from the strong electrolyte. One more thing. If they ask you, what is the concentration of common ion in the container? What is the concentration of common ion in the container? The concentration of common ion in the container net is C1. And what is C1? C1 is the concentration of H positive which you are getting from strong electrolyte. So from this particular thing, can I say the common ion concentration is entirely decided by the strong electrolyte? Right? See, the concentration of common ion is coming out to be C1 finally. Right? What was the C1? It was basically the concentration of common ion coming from strong electrolyte. So strong electrolyte is the one which decides the entire common ion concentration. So take a note of this particular thing. It's important. Concentration of common ion. Concentration of common ion is entirely decided by the strong electrolyte. So strong electrolyte is the one which governs, which decides the concentration of the common ion. I hope this is absolutely clear to you. Let's try to solve a question on the same concept. So before doing the question, tell me one thing. When a strong electrolyte is added to a weak electrolyte, both having one ion in common, what will happen to alpha value of a weak electrolyte? The degree of ionization of the weak electrolyte decreases. And this decrease in the value of alpha due to the addition of strong electrolyte to the weak electrolyte, both having one ion in common, right? That effect is what you call as common ion effect. Yeah? Perfect till here? Perfect, people? All right. Now let's try to solve certain questions. Look at the first question. The first question is calculate the concentration of each species at equilibrium in an aqueous solution. These are two questions basically. The first question is, you have got 0.1 molar NH4OH. So, you have got 0.1 molar NH4OH. NH4OH is a weak base. If it is a weak base, it's going to remain in equilibrium with its ions. Its ions are NH4 positive aqueous plus OH negative aqueous. This question will solve all your doubts if you have any. Okay. Or imagine that you have got 0.1 molar NH4 only in the container. So at time t is equal to 0, its concentration is C, which is 0.1 molar. So this is 0, this is 0. Degree of ionization, assume that alpha. So at equilibrium, it's going to be C minus C alpha. This is going to be C alpha. This is going to be C alpha. Now try to write the Kb value. Try to write the Kb value, which has to be equal to C alpha square divided by 1 minus alpha. It's a weak base, that's why Kb, right? Now what we are going to do, we are going to assume certain things. Let alpha is less than 0.05. Therefore 1 minus alpha can be taken as 1. If 1 minus alpha is taken as 1, therefore alpha is going to be under root of Kb divided by C. Therefore alpha is going to be under root of Kb. What is Kb? Kb is given 1.8 into 10 raised to the power minus 5. What about C value? C is the concentration of weak electrolyte, which is 0.1 molar, right? Now, do remember from now onwards, you'll be frequently using this. Root of 1.8 is equal to 1.34. Root of 1.8 is equal to 1.34. You'll be frequently using it. Yeah? Now, my dear students, try to understand a few more things. So, get the value of alpha from here. I would say alpha will be equal to under root of 1.8 is 1.34 multiplied by 10 raised power minus 1 will go up. It's 10 raised power minus 4. Root of 10 raised power minus 4 is 10 raised power minus 2. So, this is the value of alpha, which came out to be 0.00134. Now, check the value of alpha. Is it actually coming out to be less than 0.05? Yes, it's coming out to be less than 0.05. So, whatever is the alpha value, which you have got from here, absolutely correct. Whatever assumption you have taken, that's absolutely correct. Now, what I was supposed to calculate? I was supposed to calculate the concentration of all the ions at equilibrium. Concentration of NH4 positive at equilibrium is exactly equal to concentration of OH negative at equilibrium, and both are equal to C alpha. Look at this. This is C alpha. This is C alpha, right? C is given, alpha is given. C is 0.1. Alpha is 1.34 into 10 raised power minus 2. So the final answer is 1.34 into 10 raised power minus 3 molar. This is the concentration of all the ions in the container if there was only 0.1 molar NH4OH present in the container. That's all. Yeah. Let me know quickly in the chats if all the things are absolutely clear to you. Quickly, people. Everyone. Everyone. So the first part of the question is done. So if there was only NH4OH in equilibrium with its ions, its alpha is less than 0.05. Alpha is less than 0.05. And you got the concentration of each ion present in the container at equilibrium. Yeah? Perfect. Perfect, people. Let me know once in the chats. Now it's time to solve the second question. Now the second question will make you understand the common ion effect properly. The second question says, if 0.1 molar NH4Cl is added with, along with 0.1 molar NH4OH. Now see exactly what you'll be doing. Now the question says, already there was NH4OH in the container, which was in equilibrium with its ions, and its ions were NH4 positive aqueous plus OH negative aqueous, right? Its degree of ionization was alpha. At time t is equal to 0, its concentration was 0.1 molar. This was 0, this was 0. And at equilibrium, it was C minus C alpha. This was C alpha, this was C alpha. And when NH4OH was there in the container, which was in equilibrium with its ions, its alpha at that point of time was 0.00134, right? Which we already saw. Now, what exactly is going to happen? You are going to introduce NH4Cl in the same container. Tell me one thing. When I say NH4Cl, it is the salt of NH4 positive. And the salts of NH4 positives, they are water soluble, if you remember. And all the water soluble salts, they are strong electrolytes. So this NH4Cl, it is absolutely a strong electrolyte here. So it will undergo complete dissociation. NH4 positive aqueous plus Cl negative aqueous. Correct? Let's assume its concentration is C1, which is given to us as 0.1 molar as per the question. You can check it if 0.1 molar NH4Cl is added. Right? So this is 0 in the beginning, this is 0. Now 100% dissociation. This will be 0, this will be C1, this will be C1. Now tell me one thing. Do you see one simple thing over here? Do you see a weak electrolyte, a strong electrolyte, both having one ion in common? Absolutely. I'm seeing a strong electrolyte, weak electrolyte. Both are having one ion in common. Which effect you are going to operate? You are going to operate the common ion effect. Due to common ion effect, what will happen to the value of alpha? It was already less than 0.05. Now it will further decrease. So wherever you want to neglect alpha, you can neglect that. Yes, you can neglect that. Now, dear students, if I ask you, what is the total concentration of common ion? From here it is C alpha, from here it is C1. So it is going to be C1 plus C alpha. Now, due to common ion effect, you can neglect alpha. So instead of C1 plus C alpha, you can only write C1. Yes, you can only write C1. Now, if I want to write the Ka expression, how you are going to write it? Few minutes back only, or let's not write Ka directly. What is the new alpha? New alpha is directly going to be Ka divided by C1. Sorry, Kb by C1 in this case. Because it's a weak base, right? Kb divided by C1. If it was a weak acid, then Ka by C1. Right? So Kb value, as per the question, 1.8 into 10 raised power minus 4. C1 value is given 0.1. Right? So alpha value is equal to 1.8 into 10 raised power minus 3. Which comes out to be equal to 0.00, right? 0.00018. Perfect? 0.0018 it will come. Right? Perfect? Is there some mistake? I think yes. It is 10 raised power minus 5 here. Sorry, this is not 10 raised power minus 4. This is 10 raised power minus 5. If this is 10 raised power minus 5, it's going to be 10 raised power minus 4 here. It's going to be 10 raised power minus 4 here. Now it's going to be 0. Now it's going to be 0.0018. 0.18. Perfect. Now you are going to tell me one thing, whether this is new alpha or old alpha. Compare the old alpha and new alpha. Old alpha was 0.00134. New alpha is 0.00018. So has the alpha actually increased or decreased? Alpha has actually decreased. That's what I'm telling you. Alpha decreases due to common ion effect. What am I supposed to calculate? I'm supposed to calculate the concentration of each ion in the container. First of all, the common ion is NH4 positive. So tell me the net common ion concentration finally in the container. It was supposed to be C1 plus C alpha, which is coming out to be C1 only, right? And C1 value, that's already 0.1 molar. Absolutely correct. Now second, concentration of OH negative in the container. Concentration of OH negative is going to be C times alpha. But this alpha is not old alpha, it is the new alpha. C value is equal to 0.1. Alpha is 1.8 in 10 raised power minus 4. So the final value comes out to be at the end 1.8 in 10 raised power minus 5 into 10 raised power minus 5 molar. So this is the concentration of OH negative in the container at the end. I hope you got the concept of the common ion effect. If you actually got it, let me know once in the chats. Then only I'll be solving one more question with you. Quickly. Quickly, my dear students. Everyone in the chats. Is every single thing clear till here? Look at this question now. Look at one more question. Calculate the concentration of H positive and CH3CO negative at equilibrium. If 0.5 molar HCl is added in an aqueous solution containing 0.1 molar CH3COH. Similar pattern of question. Let's give it a try. Let's try to understand this common ion effect a bit more in detail now, right? By solving this question, absolutely everything will be clear. Now, as per the question, you have got CH3COH aqueous in the container. Since it's a weak acid, so it's going to remain in equilibrium with its ions. Its ions are CH3CO negative aqueous plus H positive aqueous, right? Now, at time t is equal to 0, the concentration of CH3COH is C. How much is that? That's 0.1 molar as per the question. So this will be 0, this will be 0. Degree of ionization alpha. So at equilibrium, it's going to be C minus C alpha. This is C alpha, this is C alpha, right? Right, people? Now, my dear students, in the same container, what you're doing? You're adding HCl in the same container. HCl is an example of a strong electrolyte. So it will undergo complete dissociation as H positive aqueous plus Cl negative aqueous. Now, the concentration of HCl in the beginning has been kept as 0.5 molar. So this will be initially 0, this will be 0. Now 100% dissociation. This will be 0, this will be C1, this will be C1. Now try to understand a concept. Do you see? Weak electrolyte and a strong electrolyte. Weak electrolyte, strong electrolyte. Both having one ion in common. That's H positive. So which effect is going to operate here? Again the common ion effect is going to operate. Due to common ion effect, this alpha value will further decrease. Already it was less than 0.05. Now it will further decrease, right? So wherever you want to neglect alpha, you can do that. So tell me first of all, what is the concentration of the common ion? H positive concentration from here is C1, from here is C alpha. So it has to be C1 plus C alpha. But which finally you have to write as C1 only, right? What is the new alpha? New alpha is going to be Ka divided by C1. Ka value as per the question, 1.8 into 10 raised power minus 5 divided by C1 value, that's 0.5, right? Which comes out to be 3.6 into 10 raised power minus 5. This is the value of new alpha. Now, what is the concentration of the common ion? Common ion is H positive. The net common ion concentration is C1 basically, and C1 is equal to 0.5 molar. If I ask you, what is the concentration of CH3CO negative in the container at the end? That is C times alpha. So C times alpha. C value is 0.1 and alpha is how much? Alpha is 3.6 into 10 raised power minus 5 now. So the value comes out to be 3.6 into 10 raised power minus 6 molar. So these were the two things which you were supposed to calculate, I believe, right? Yeah? Is it clear, people? Quickly. Is it clear to everyone? Without using pen and paper, tell me the answer of this question. Without using pen and paper, tell me the answer of this question. Without using pen and paper. Calculate the concentration of H positive at equilibrium if 0.1 molar HCl is added in an aqueous solution containing 0.1 molar CH3COH. Without using pen and paper. Strong electrolyte, weak electrolyte. Both are having one ion in common. That one ion is H positive. Concentration of common ion is decided by the strong electrolyte. Strong electrolyte HCl undergoes dissociation as H positive plus Cl negative. Right? So, concentration of H positive is decided by strong electrolyte HCl, which undergoes dissociation as H positive plus Cl negative. Its concentration was 0.1. So, its concentration will be 0.1 molar. The equation is done here only. Right? Agreed to this? Agreed, people? Yeah, or you can have a detailed approach the way I have been solving the questions. In the similar way, you can try this question as well, writing both the reactions, etc., etc. Gautam, just watch the video which I've taken for the test series, right? Just watch that video. I've given the entire syllabus for the first 7 tests. Just watch that video. I don't remember what is the syllabus of the upcoming test. Just watch that video and see. Okay? Perfecto. Moving ahead. There is something called as Oswald's dilution law. What is Oswald's dilution law all about? It's again very simple, right? Let me try to make you understand what is Oswald's dilution law. As per this law, on dilution, degree of ionization. Upon dilution, degree of ionization of a weak electrolyte increases. With the dilution, the degree of ionization of a weak electrolyte increases. What does that mean? Try to understand. For example, you have got a weak electrolyte as AB. This is a weak electrolyte. If it is weak, it's going to remain in equilibrium with its ions. Its ions are A positive aqueous plus B negative aqueous. Let's assume the degree of ionization is alpha. Let's assume initially its concentration is C. This is 0, this is 0. So at equilibrium, it's supposed to be C minus C alpha. This is supposed to be C alpha. This is supposed to be C alpha, right? Let's assume that the ionization constant of this weak of this weak electrolyte is Ki, which will be for sure C alpha square divided by 1 minus alpha. Now again, let's assume that alpha is less than 0.05. Therefore, 1 minus alpha will be taken as 1 from here, and alpha value will be equal to under root of Ka by C. Alpha value will be equal to under root of Ka by C. Right? Now what exactly we are going to do? Try to understand. So first of all, I had a container in which the weak electrolyte was in equilibrium with its ions. This is the container in which the weak electrolyte is in equilibrium with its ions, right? Now, if I ask you what is concentration basically, concentration is number of moles per unit volume of the system. Number of moles per unit volume of the system in liters. Now, dear students, for example, if you are adding more solvent here is water, for example, right? If you are adding water into the container, so what you are doing? You are doing dilution. By the addition of water, what will happen to the volume of system? Volume of system will increase. If volume of system increases, concentration will decrease. Both are inversely proportional. If concentration decreases, that means alpha value will increase. Alpha value will increase. That's something which I wrote over here. Upon dilution, degree of ionization of a weak electrolyte, what happens to it? It increases, right? Upon dilution, degree of ionization of a weak electrolyte, that increases. So upon dilution, upon the addition of water here in this particular scenario, this weak electrolyte gets more and more ionized into its ions. It gets more and more ionized into its ions. Right? Can I say upon continuous dilution, this weak electrolyte will be continuously getting dissociated into its ions. Can I say a scenario will come when 100% of this electrolyte would have got dissociated into its ions? That particular dilution is something which we call as infinite dilution. So at infinite dilution, I must say this weak electrolyte would have got completely dissociated. So at infinite dilution, the weak electrolyte will be behaving like the strong electrolyte, So I can say at infinite dilution, the degree of ionization of the weak electrolyte, that becomes 1. So it now behaves like the strong electrolyte, right? I hope this is clear. I hope this is clear to everyone, right? This is the scenario which I gave you. At infinite dilution, the weak electrolyte behaves as a strong electrolyte. Perfect, people? Is this super duper clear to you? Quickly. Let me know quickly in the chats, every one of you. Quickly. Yes, Anish, it is in electrochemistry only. I mean, in electrochemistry, you learn the same concept, right? Effect of dilution on molar conductivity and equivalent conductivity for strong as well as weak electrolytes. Perfect. Now, ionic product of water. Again, one important topic. Ionic product is represented by Kw first of all. Now, what is ionic product of water? Try to understand what exactly I'm going to say. This is again some complete basic thing. Try to understand. My dear students, for example, you have got water, pure water you have, right? You have taken pure water in the container. Let me tell you, pure water, it's again considered as a weak electrolyte. Pure water, it is again considered as a weak electrolyte. If pure water is considered as the weak electrolyte, so it will also remain in equilibrium with its ions. Its ions are H positive aqueous and OH negative aqueous. Or you can write H3O positive aqueous, OH negative aqueous. By solvers, right? Yeah. So I'm talking about pure water. Pure water is again the example of a weak electrolyte, which is going to remain in equilibrium with the ions. Now, if this pure water is the example of weak electrolyte, can you write its ionization constant expression? Absolutely. Concentration of H positive at equilibrium raised power 1, concentration of OH negative at equilibrium raised power 1 divided by concentration of H2O liquid, right? Now you can write it like this: Ki multiplied by concentration of H2O is equal to concentration of H positive multiplied by concentration of OH negative. Now, my dear students, this particular term, it's constant, right? This particular term, it's constant. So constant multiplied by constant makes it a new constant, that's Kw. So Kw is nothing. It is the product of concentration of H positive and OH negative, right? This particular expression is valid at all temperatures. It is valid at all temperatures. It is valid at all temperatures, this particular expression. Kw, which is what you call as ionic product of water. It is defined as the product of H positive concentration and OH negative concentration in the container. That's all. Yeah? But try to understand one thing. My dear students, at 25 degrees centigrade, do remember a few things now. At 25 degrees centigrade, the concentration of H positive is equal to the concentration of OH negative in the container at 25 degrees centigrade. Concentration of H positive and OH negative, both are equal to 10 raised power minus 7 mole in the container. But at 25 degrees centigrade, if concentration of H positive OH negative at 25 degrees centigrade is 1 molar, then what's going to happen? I must say, Kw will be written as, ionic product of water will be written as concentration of H positive multiplied by concentration of OH negative, 10 power minus 7, 10 power minus 7, which makes it 10 raised power minus 40. But this equation is only valid at 25 degrees centigrade, when water is kept at 25 degrees centigrade, right? Perfect. Now, guys, try to understand a few things now. Have you ever heard of pH? Okay, leave pH aside. Let me tell you what this P stands for. What is P? This small p. It is just a mathematical operator. It is just a mathematical operator which stands for minus log. Minus log is represented by P basically. In short, minus log is represented by P. For example, you are writing pH. What does it mean? P stands for minus log. So that means I'm talking about minus log of H positive concentration. For example, if I write POH, P stands for minus log. that means I'm talking about minus log of OH negative concentration. If I'm writing P of Ka, that means I'm talking about minus log of Ka. So what is P basically? P is nothing, it is just the mathematical operator which stands for minus log, right? Now, what exactly I'm going to do? I'm going to multiply this equation throughout by minus log. Multiplying throughout by minus log. It becomes minus log of Kw is equal to minus log of H positive concentration, OH negative concentration, which is equal to minus log of 10 raised power minus 14. Now minus log of Kw is simply called as P of Kw is equal to, when you split it, log of m into n makes it log of m plus log of n. It finally becomes pH plus POH, right? And this term minus log of 10 raised power minus 14, it comes out to be 14. It becomes 14 because log of m raised power n is n log m. But this particular equation, again I'm telling you, it's valid only when water is kept at 25 degrees centigrade, right? So at 25 degrees centigrade, this particular equation is valid. P of Kw is equal to pH plus POH. That's equal to 14, right? Perfect. Perfect, guys. Now tell me one thing. Tell me one simple thing, which I'm going to tell you here. Since Kw is equal to concentration of H positive multiplied by concentration of OH negative, do remember, on increasing the temperature, the value of Kw increases. When you increase the temperature, on increasing the temperature, the value of Kw, it increases. Do remember it, okay? Do remember it. So let me know once in the chat if it is clear, quickly. Quickly, guys. Yes? Perfect. Perfect. Try to understand a few more things. I'm going to tell you one important thing now, okay? One important thing. I'm going to tell you now. Try to understand that carefully. What is that important thing? Have a look. I'm writing a statement. The statement is, upon increasing the temperature, pH scale shrinks. pH scale shrinks. This is one important concept. Why is it important? There is a logic for that. Why is it important? For example, I'm asking you a question like this. You have got two glasses, right? Both containing water. This is H2O liquid. This is H2O liquid, right? Now this H2O liquid is at 25 degrees centigrade. This H2O liquid is at, for example, 35 degrees centigrade. Can you let me know whose pH will be more, whose pH will be less? Just say it. What do you think? Both the containers will be containing water, right? One is at 25 degrees centigrade, one is at 35 degrees centigrade. So where do you see the pH of water more, at 25 or 35? Quickly, guys. With this, I should have some water as well. Where do you see pH of water more? So a lot of people are saying pH at 25 degrees centigrade will be more and pH at 35 degrees centigrade will be less. pH more, what does that mean? Basic. pH less, does that mean acidic? So does that mean when I'm drinking hot water, does that mean I'm drinking acid? Are you trying to say that? Okay, just kidding. Try to understand what I'm going to say. Try to understand what I'm going to say. I've written a statement, on increasing the temperature, pH scale shrinks. So basically, at 25 degrees centigrade, pH scale varies from 0 to 14. and in the middle, the 0.7 is here, which represents neutral, Before this, it represents acidic part, and after this, it represents basic part. Correct? At 25 degrees centigrade. Now, for example, the same water is at 35 degrees centigrade. For example, the same water is at, 35 degrees centigrade. Right? So, have I increased the temperature? Absolutely, I have increased the temperature. Upon increasing the temperature, pH scale shrinks. pH scale was initially from 0 to 14. Now, for example, imagine that the pH scale will now be from 0 to 13 only. The pH scale has shrinked a bit. Now, the middle point over here is 6.5 only. Middle point is 6.5. So, in this particular scale, on this particular scale, the 6.5 represents neutral. Before this part represents the acidic part and this part represents the basic part. Right? Right, people? Now, what was I doing? I was increasing the temperature of water. When you increase the temperature of water, Kw value increases. Kw value increases. Kw increases, that means H positive as well as OH negatives increase. On increasing the temperature, H positives as well as OH negatives increase. My dear people, the stoichiometric coefficient is 1:1. On increasing the temperature, H positives as well as OH negatives increase. What does that mean? That over here means the concentration of H positive and OH negatives are increasing by equal amounts. Right? The concentration of H positive and OH negative upon increasing the temperature are increasing by equal amounts. Right? If the concentration of H positives and OH negatives are increasing by equal amounts, what will happen to neutrality? Neutrality will remain the same because the concentration of H positives and OH negatives, they are increasing by equal amounts on increasing temperature. So neutrality is going to remain the same, but at 25 degrees centigrade, 7 used to represent the neutral solution. At 35, for example, 6.5 represents the neutral. Upon increasing the temperature, neutrality has to remain the same. Right? So that means to have the same neutrality, the pH has to decrease from 7 to 6. Because 7 was used to represent neutral at 25. But at 35, 6.5 represents neutral. Neutrality remains the same. So in order to show the same neutrality, pH will decrease. Right? So what should be the answer? Upon increasing the temperature, pH scale shrinks. Let me tell you, pH scale shrinks. Upon increasing the water, on increasing the temperature, pH of water decreases. But does that affect the neutrality? But neutrality of water remains the same. Right? But the neutrality of water remains the same. I hope this point is clear to you. Yeah? Let me know once in the chats if it is super clear. One more thing. If the concentration of H positives and OH negatives in the solution is equal, the solution is going to be neutral. If H positive concentration is greater than OH negative concentration, it's going to be acidic. If it is less, it's going to be basic. This is something which you all must be knowing already, right? I'm not going to discuss about this one. I hope all these things are absolutely clear to you, right? So before talking about the pH, let's take a small break, right? And after that, we are going to discuss pH. Right, people? So let me know once in the chats if all the things are super clear to you. Let me know once in the chats if all the things are super clear to you. And the break only I'm going to give you if you guys will be back on time. Yes? The time now is 7:32. So let's start the session again at I'm giving you a break of 15 minutes. Be back on time, okay? Have your dinner or whatever. And after that, we'll talk about the pH. pH is the most important topic of this particular chapter. So I'll see you all at 7:55. Till then, you take care. So guys, can you all hear me again? Is everyone back? Yes? Is everyone back? Perfect, perfect. You are on time. Yeah? You are on time. Exactly, back to the session. So I hope whatever I've taught you till now, every single thing is absolutely clear to everyone. Yeah? Now, my dear students, we are going to discuss one of the most, I would say the most important topic of the chapter, that is calculation of pH. How do we calculate pH of different solutions? So one by one, we are going to discuss all the categories in it, right? And again, we'll be starting from the basics itself, from the zero itself. So my dear students, the first category here, in order to calculate the pH, the first category which I'm going to discuss with you, what is that? That is calculation of pH of a strong monoprotic acid or a base. First of all, whenever you are supposed to calculate pH of a solution, whenever you are supposed to calculate pH of the solution, what does first of all that mean? You know, P stands for minus log. Minus log of what? Minus log of net H positive ion concentration. So whenever you are supposed to calculate pH of any solution, your first point always will be to calculate the net H positive ion concentration in the solution. Once you get the total H positive ion concentration in the solution, take minus log of it. Whatever the value you'll be getting, that's going to be the pH of the solution. Right? So dear students, in order to calculate the pH of the solution, what do you need? You need the H positive ion concentration in the solution. Once you get the H positive ion concentration in the solution, take minus log of it, get the value, that's going to give you the pH. That's all. Right? Now, dear students, the first category is calculate the pH of strong monoprotic acids and bases. What does it mean? See, these are 6 questions over here. These are 6 questions over here. By solving these questions, you'll exactly get the idea of how do we calculate pH of strong monoprotic acids or bases. So, dear students, have a look on the first case. We are given with 0.1 molar HCl aqueous solution. We are given with 0.1 molar HCl aqueous solution. We are supposed to calculate pH of this particular solution, right? Now, first thing, if I ask you, HCl, is it a strong acid or weak acid? It's absolutely a strong acid. Strong acid means it's a strong electrolyte. If it is a strong electrolyte, it would have got completely dissociated into its ions. So basically, when you will introduce HCl in water, it will completely get dissociated into its ions, right? Because it's a strong electrolyte. Now, dear students, if I ask you, at time t is equal to 0, what was the concentration of HCl that was given to us? 0.1 molar. So this was 0, this was 0. Now it's a strong electrolyte, it will get completely dissociated, right? So I'll be left with nothing of this HCl. Now 1 mole of HCl gives 1 mole of H positive. So 0.1 molar is going to give me 0.1 molar of HCl. H positive. Similarly, 0.1 molar of Cl negative. So can I say I got the concentration of H positive in the solution? The concentration of H positive in the solution came out to be 0.1 molar. That means 10 raised per minus 1 molar. And since you got the H positive ion concentration in the solution, you can directly calculate pH. P stands for minus log. So minus log of what? Minus log of H positive concentration, which comes out to be minus log of 10 raised per minus 1. Log of m raised per n is n log m. So minus 1 comes to the front. Minus becomes plus. So the value comes out to be 1. And log of 10 is 1 itself. So I would say pH of the solution over here that was given to us, that's absolutely 1. Right? Perfect. Very simple. Now look at the second one. 10 raised per minus 3 molar HCl. So I'm given with 10 raised power minus 3 molar HCl aqueous solution. Get its pH. Get the pH of this solution. Now, if I talk about HCl, it's again a strong electrolyte. When you introduce it into water, it will get completely dissociated. It will get completely ionized, right? The initial concentration of HCl was 10 raised power minus 3 molar. So this was 0. Even this was 0. Now it will be getting 100% ionized. This will be 0. 1 mole of HCl gives 1 mole of H positive. So 10 power minus 3 molar will give 10 power minus 3. Even this will be 10 raised power minus 3 molar. Now, my dear students, you got to know the H positive concentration in the solution. That's 10 raised power minus 3 molar. Now calculate the pH. P stands for minus log of H positive concentration. So the final answer will come out to be 3. So pH of this particular solution is simply 3. That's all. Right? Similarly, you can calculate for this one. Easy. Now, look at this particular case. 10 raised power minus 7 molar HCl. Now try to understand. Here's a trick. Next case is 10 raised power minus 7 molar HCl aqueous solution. Try to understand. First of all, when I introduce HCl into water, I would say this HCl will dissociate into H positive and Cl negative. When you introduce HCl into water, you will get H positive aqueous and Cl negative aqueous. Correct? Now, my dear students, at time t is equal to 0, what was the concentration of HCl? That was 10 raised power minus 7 molar. This was 0. This was 0. Now it's a strong acid, complete dissociation. This will be 0. This will be 10 raised power minus 7. This will be 10 raised power minus 7. Right? So what is the H positive concentration which you got over here? H positive concentration is coming out to be 10 raised power minus 7 molar. Right? In the solution, we got to know H positive concentration is 10 raised power minus 7 molar. So if I ask you to calculate pH, P stands for minus log of H positive. The value comes out to be 7. Right? So pH of this solution has to be 7. But if you think logically, are we given with acidic? Is this acidic solution or basic solution? It is 10 raised power minus 7 molar HCl aqueous solution. So it is acidic solution. Its pH is supposed to be less than 7, but it's coming out to be 7. So that means there's a mistake which we'll be doing. There's a mistake which we are doing here. See, following the general procedure, the pH of this particular solution is coming out to be 7, but it should be less than 7. Whenever by following this particular procedure, the pH of acidic solution comes out to be 7 or greater than 7. At that point of time, what exactly we need to do? Try to understand. See guys. See. HCl you are introducing in water basically. Right? HCl you are introducing in water. Since water is already a weak electrolyte, which is in equilibrium with its ions, H positive, H negative. So can you let me know already in the water what was the H positive concentration which was already there in the water? That was already 10 raised power minus 7 molar at 25 degrees centigrade. And this is the H positive concentration which is coming from acid. Already in the container, the concentration of H positive was 10 raised power minus 7 molar. Now, in the water, you are introducing the HCl, right? So, concentration of H positive coming from HCl, that's 10 raised power minus 7. Concentration of H positive, which was already coming from water, was 10 raised power minus 7 molar. If I ask you, what is the net H positive ion concentration in the container? Net H positive ion concentration, total H positive ion concentration in the container will be this plus this, which is 2 times 10 raised power minus 7 molar. This is the total H positive ion concentration in the container. Now calculate the pH of the solution. P stands for minus log of net H positive ion concentration in the container, which is minus log. This is 2 into 10 raised power minus 7. Now a bit of maths is used here. Minus log of m into n. It is log m plus log of n. So minus, I'm writing as such. This is 0.3. Log of 2 is 0.3. Log of m raised power n. N log m. So minus 7 comes to the front. So the final answer comes out to be 6.7. So 6.7 is the actual pH of this particular solution which we have taken over here. Right? So whenever this sort of a question comes, do not make a mistake. Right? And when do you have to use this kind of the procedure? If the pH of the acid comes out to be 7 or greater than 7, at that point of time, you have to take into consideration the H positives which were already coming from water. You have to consider those H positives as well, which were already there in the water. Perfect. I hope this is clear. I hope this is clear. Moving on to one more. 10 raised power minus 4 molar NaOH. 10 raised power minus 4 molar NaOH. 10 raised power minus 4 molar NaOH aqueous solution. How do we get its pH? First of all, my dear students, NaOH, how will it undergo dissociation? NaOH will undergo dissociation as Na positive plus what? Plus OH negative. This is how it will undergo dissociation. Now at time t is equal to 0, what is the concentration of NaOH? 10 raised power minus 4 molar. This is 0. This is 0. Now tell me, is NaOH strong base or weak base? It's a strong base. It will get completely ionized. This will be 0. 1 mole gives 1 mole. 10 power minus 4 gives 10 power minus 4 molar. Similarly, this will be 10 raised power minus 4 molar. Can you let me know what is the OH negative concentration which you are getting here? It is 10 raised power minus 4 molar. My dear students, if you got the OH negative concentration, can't we calculate POH? Absolutely, we can calculate POH of the solution. P is minus log. So minus log of OH negative concentration. So it becomes minus log of OH negative concentration is 10 raised power minus 4. The value comes out to be 4. So this is POH. But was I supposed to calculate POH? No. I was supposed to calculate pH. Already you know, pH plus POH at 25 degrees centigrade. That's 14. So pH will come out to be 14 minus POH. So 14 minus 4 comes out to be 10. So 10 is going to be the pH of this resulting solution. I hope this is clear. Right? Let's have a look on one more example in which you can do a mistake. 10 raised power minus 8 molar NaOH. 10 raised power minus 8 molar NaOH. 10 raised power minus 8 molar NaOH aqueous solution. Calculate its pH. How exactly you're going to do it? Again, my dear students, a similar procedure. So first of all, you know, your NaOH, when you introduce it into water, how it's going to get dissociated. It will undergo dissociation as Na positive aqueous plus OH negative aqueous. This is how it will undergo dissociation. Now tell me one thing. Initially, at time t is equal to 0, what is the concentration of NaOH? 10 raised power minus 8 molar. So this has to be 0. This has to be 0. Now, it is a strong base. It will get completely dissociated. This will be 0. This will be 10 raised power minus 8 molar. This is again 10 raised power minus 8 molar. Right? Now, you can do a mistake here. And what is the mistake? Let's wait for it. See guys, if I ask you, what is the OH negative concentration which is coming from the base? 10 raised power minus 8 molar. If you got OH negative concentration, can't we calculate POH, which is minus log of OH negative concentration? The value comes out to be 8. So if POH is coming out to be 8, that means pH will be 14 minus 8. That means pH should be 6. pH should be 6. pH is equal to 6. Does it represent acidic or basic solution at 25 degrees centigrade? It represents acidic solution, right? But is NaOH aqueous? Is it acidic or basic? It is actually basic. But from here, it's coming out to be acidic. That means some mistake we are doing. What is that mistake? Try to rectify it. Try to rectify it, dear students. Basically, when you are introducing NaOH in water, already water is a weak electrolyte. So from water, already there will be some OH negatives, which will be in equilibrium with H2O, right? So already there were OH negatives present in the container, which have come from water. How much was that? 10 raised power minus 7 molar at 25 degrees centigrade. Already these many OH negatives were there in the container. Now you are adding NaOH into that water. So OH negative concentration which is coming from NaOH, that is 10 raised power minus 8 molar. Already in the container there were 10 raised power minus 7 molar OH negatives due to water. Now this much molar concentration of OH negative is coming from NaOH. Now if I simply ask you, what is the net OH negative concentration in the container? You will say this plus this, right? 10 raised power minus 8 plus 10 raised power minus 7. This is the total, this is the net OH negative concentration which is present in the container. Now, my dear students, try to understand one thing. If I take 10 raised power minus 8 common, it's going to be 10 raised power minus 8 divided by 10 raised power minus 8 plus 10 raised power minus 7 divided by 10 raised power minus 8. Correct? This is the net OH negative concentration. So I can say net OH negative concentration is equal to 10 raised power minus 8. This value is 1 plus 10 raised power minus 8 goes up, it comes out to be 10. So 10 plus 1 is 11. So it's 11 into 10 raised power minus 8 molar. This is the net OH negative concentration which is present in the container. Once you get the net OH negative concentration, you can easily calculate POH. P stands for minus log. P stands for minus log. Minus log of net OH negative concentration, which is minus log of 11 into 10 raised power minus 8. You can write it like this, minus log of 11 plus log of 10 raised to the power minus 8. Now a bit of calculation is needed. A bit of calculation is needed. I'm calculating it over here. So it's going to be minus log 11. Do remember it's 1.05. Log of m raised power n. And log m, so minus 8 comes to the front. So the value will be 6.95. So this 6.95, what is it? It is the POH basically. It is the POH. Now calculate the pH. It's going to be 14 minus POH. The value has to be 7.05. So 7.05 is the actual pH of the solution which we were supposed to calculate. So whenever you see this sort of a question, do not commit a mistake, right? Do not commit a mistake. So in short, whenever by following the general procedure, pH of the basic solution comes out to be 7 or less than 7, at that point of time, take the OH negatives coming from water into consideration as well, and then calculate the net OH negative concentration, get the POH, and finally get the pH. That's all. Yeah? Perfect. I hope these sort of things you can easily do. You can easily solve. Now, there are a few more mistakes you might do in the basic things. For example, you have got 0.1 molar H2SO4 aqueous solution. Just tell me one thing. How H2SO4 undergoes dissociation when you introduce it into water? It will get dissociated as 2 times H positive aqueous plus SO4 di negative aqueous. Right? That's how it will undergo dissociation. Tell me one thing. At time t is equal to 0. What is the concentration of H2SO4 that's given to me? 0.1 molar. This is 0. This is 0. Now H2SO4, strong acid, strong electrolyte, completely dissociated. So this will be 0. 1 mole gives 2 moles. 0.1 molar will give 0.2 molar. 1 mole gives 1 mole. 0.1 will give 0.1 molar. So if I ask you, what is the concentration of H positive which we are getting here? Concentration of H positive which we are getting here, that is 0.2 molar. That means 2 into 10 raised power minus 1 molar. What are we supposed to calculate? We are supposed to calculate pH. P stands for minus log. Minus log of what? Minus log of H positive concentration. So minus log of H positive concentration is 2 into 10 raised power minus 1. Now a bit of maths is needed. That's all. A bit of maths is needed. So I would say pH has to be equal. Minus, you're writing as such, log of m into n. It becomes log of m plus log of n like this. So pH will come out to be minus. Log of 2 is 0.3. Log of m raised power n. And log m. So the value comes out to be 0.7. So 0.7 is going to be the pH of this particular solution. Yes? Yes, these lectures are enough. Is it clear, guys? Is it clear? Say yes or no in the chats quickly. All right, one more thing. Look at the second question. Look at the second question. BaOH whole twice. How will it undergo dissociation? Ba di positive plus 2 times OH negative. So if I ask you directly, what will be the OH negative concentration? It will be 2 times 10 raised power minus 3. This is the OH negative concentration. If I ask you what is POH, minus log of 2 into 10 raised power minus 3, which is minus log 2 is 0.3 and log of m raised power n. It will be minus 3 at the end. The value is 2.7. So POH is 2.7. So pH is going to be 14 minus POH. The value has to be 11.3. Right? Done and dusted. Nothing to worry about these questions. Perfect. Perfect, people? Is that clear? So these sort of mistakes you can do, right? So whenever you solve these basic equations, try to dissociate your electrolyte in a proper way. Do not just write H positive and OH negative. Do not just write H positive SO4 dinegative. No. Yeah. Perfect. Is that clear till here? Say yes or no in the chats. Say yes or no in the chats. Say yes or no in the chats quickly. Now comes one more case. Calculation of a pH of a mixture of strong acids or strong bases. This particular topic I'm going to break in 3 parts. I'm going to break in 3 parts. Case 1. For example, you are mixing 2 acidic solutions, strong acid 1 plus strong acid 2. Let's say in the container you have got 2 acidic solutions. After mixing these acidic solutions, I will be getting a resulting solution. And for example, I'm supposed to calculate the pH of this particular resulting solution. Let's say I'm supposed to calculate pH of this resulting solution. This is one more case. This is the first case over here. For example, you have got a mixture of 2 strong acids. After mixing 2 strong acids, we'll be getting a resulting final solution. How do we calculate pH of that final resulting solution? That's important. How do we do it? Try to understand how exactly we are going to do it. Yeah? Try to understand how exactly we are going to do it. Before showing you the procedure of solving the question, let me teach you a few more things. My dear students, let me tell you. Since you know molarity is equal to number of moles of solute divided by volume of solution in liters. I assume everyone would be knowing this. Molarity of the solution is equal to number of moles of solute divided by volume of solution in liters, right? So from this particular equation, can't we calculate number of moles of solute? Molarity of the solution multiplied by volume of solution in liters. Agreed? Let's say you are given with a solution whose molarity you know, whose volume in liters you know. You just have to multiply these two. You'll be getting the moles of solute in the solution. In the similar way, in the same equation, if you use volume of the solution in ml, then you'll be calling it as number of millimoles of solute. You'll be calling it as number of millimoles of solute. So these are the 2 things which I would want all of you to remember right now. Why is that? Why is that? You'll get the idea in some time. So first, let me know in the chats if all the things are clear till here. Yeah? Okay. Now guys, understand what exactly I'm going to do. I'm going to start with a question so that you can understand it properly. Calculate the pH of the following mixture. Try to understand what exactly you are mixing. This is the acidic solution. This is the acidic solution. So basically, you're mixing 2 strong acids, H2SO4, HCl. You're mixing 2 strong acids, right? After mixing these 2 strong acidic solutions, you'll be getting a resulting solution. You'll be getting a final solution whose pH you have to calculate. Now, how exactly? How exactly? Try to understand. Try to understand properly. First of all, the first solution is your H2SO4 aqueous solution. The first solution is your H2SO4 aqueous solution. Can you let me know how this H2SO4 aqueous solution would have undergone dissociation? How this H2SO4 would have undergone dissociation? It is a strong acid, this is the strong acid. I'm talking about the first acid. This H2SO4 would have undergone dissociation as 2 times H positive aqueous plus SO4 dinegative aqueous. This is how it would have undergone dissociation. In the similar way, how this HCl would have undergone dissociation? HCl would have undergone dissociation as H positive aqueous plus Cl negative aqueous. Correct? Now, my dear students, try to understand. Time t is equal to 0. The first solution which we have, I know its molarity, I know its volume in ml as well. Molarity of the solution multiplied by volume of solution in ml. What does it give me? It gives me number of millimoles of solute. Number of millimoles of solute. So if I ask you, how many millimoles of H2SO4 do we have? This multiplied by this, the value comes out to be 200. So we have got 200 millimoles of H2SO4 in the beginning, right? This will be 0. This will be 0. Correct? Now, dear students, H2SO4, it's a strong acid. It will undergo dissociation, complete dissociation. So I'll be left with 0 millimoles of H2SO4 in the solution. 1 mole of H2SO4 gives 2 moles of H positive. So 200 millimoles will give 400 millimoles of H positive. Right? Similarly, 1 mole gives 1 mole. So 200 will give 200. So my dear students, tell me one thing. How many millimoles of H positive? How many millimoles of H positive we are getting from H2SO4? How many millimoles of H positive we are getting from H2SO4? We are getting 400 millimoles of H positive from H2SO4, right? Similarly, tell me how many millimoles of HC, how many millimoles of H positive will be getting from HCl? You can do that as well. See, initially at time t is equal to 0. See, the molarity of HCl is given, volume of HCl in ml is given. So this multiplied by this, molarity multiplied by volume in ml, that gives me the millimoles of solute. So we have got 200 millimoles of HCl in the beginning, right? So this has to be 0, this has to be 0. Now HCl, complete dissociation, 0. 1 mole gives 1 mole. So from 200 millimoles, you will be getting 200 millimoles of H positive. Similarly, this will be 200 millimoles of Cl negative. So if I ask you, how many millimoles of H positive you are getting from HCl, you are getting 200 millimoles of H positive from HCl. Now, my dear students, if I ask you how many total millimoles of H positive are there? How many total millimoles of H positive are there in the final solution? 400 plus 200 makes it 600. So in total, in the final solution, there are 600 millimoles of H positive, right? There are 600 millimoles of H positive. Can I say millimoles divided by volume, that gives me the molarity? Millimoles divided by volume, that gives me the molarity. So if I ask you, what is the molarity of H positive in the final solution? Molarity means concentration. Molarity means concentration. If I ask you, what is the net H positive concentration? Total H positive concentration in the final solution. It's going to be millimoles, total millimoles of H positive divided by total volume of the resulting solution. 400 plus 400 makes it 800. So it's going to be 3 by 4. So 3 by 4, what is it? It is the net H positive ion concentration. It is the total H positive ion concentration, right? Since you got the total H positive ion concentration, how do you calculate pH? pH stands for minus log of net H positive ion concentration, which is minus log of P divided by 4, which is minus times log of M by N is a log of M minus log of N, right? So it is minus. Log of 3 is, how much is log of 3? 0.47. Log of 4 is 0.6. The final value comes out to be 0.13. So 0.13 is the pH of the final solution. 0.13 is the pH of the resulting solution. I hope this sort of a question you can easily solve from now onwards. So do remember, get the millimoles of H positive from first acid, get the millimoles of H positive from the second acid, get the total millimoles of H positive in the resulting solution, divide that by the total volume in ml, you'll be getting the concentration, net H positive ion concentration. And then you can easily get the pH of the resulting solution, minus log of net H positive ion concentration. That's all. Agreed? Is this clear to every single guy? Quickly in the chats. Quickly in the chats, people. One more type of the question. A 50 ml solution of strong acid of pH 1. So we have got a strong acid whose pH is 1. Whose pH is 1. Volume is equal to 50 ml. Right? Is mixed with 50 ml solution of strong acid. We have got one more strong acid whose pH is 2 and whose volume is how much? Whose volume is 50 ml. Now you are mixing them. After mixing them, you'll be getting a resulting solution and you have to calculate pH of this particular resulting solution. It's an easy question. It is an easy question, guys. Try to understand. pH of the first acidic solution is 1. Does that mean H positive concentration is equal to 10 raised power minus 1 molar, right? pH of the second acidic solution is 2. So does that mean H positive ion concentration from this particular solution is going to be 10 raised power minus 2 molar? Agreed? Right? Simple. Molarity multiplied by volume in ml, it gives me millimoles. So what about the millimoles of H positive coming from first strong acid? This multiplied by this value is 5. What about the millimoles of H positive? Millimoles of H positive coming from second solution. This multiplied by this, it is 0.5. If I ask you how many total millimoles of H positive are there in the resulting solution, this is 5 plus 0.5, which makes it 5.5. These are the total millimoles of H positive. These are the total millimoles of H positive in the resulting solution. Tell me what is going to be the net H positive ion concentration in the final solution. Total millimoles of H positive divided by total volume. Total volume is 50 plus 50 makes it 100. Right? If you got the net H positive ion concentration, calculate the pH of the resulting solution, which is minus log of net H positive ion concentration. So pH has to be equal to minus log of net H positive concentration is 5.5 divided by 100 molar. So pH has to be equal to minus times log of m by n, which is log of m minus log of n. Now, as per the question, it's mentioned that log of 5.5, that is 0.74, minus log of 100. Log of 100 can be written as log of 10 raised power 2, which is 2 log 10. So it's going to be final 2. So the final answer is going to be 1.2x. 1.26. 1.26 is going to be the pH of the final resulting solution. I hope you can solve this sort of equation from now on. Right? Is it clear to everyone? Is it clear to everyone, people, quickly? Yes? So what was this part? This was the pH of a mixture containing 2 strong acids. This was the pH of a mixture containing 2 strong acids. In the similar way, let's say you have got 2 strong bases. So let me mark the heading as case 2. 2 strong bases. Strong base 1 plus strong base 2. Right? You're mixing them. You have got a mixture of 2 strong bases. How do you calculate pH of the mixture? How do you calculate the pH of the mixture? Right? Which is formed when 2 strong bases react. When 2 strong bases basically are present in the same container. How do we do it? Similar type of scenario this is. Similar type of scenario. Try to understand what exactly I'm going to say. Just try to understand what exactly I'm going to say. For example, my dear students, you have got a strong base as BOH. BOH. Or let me call it as B1OH. It's a strong base. Or if not like this, let me frame a question over here. Let me frame a question over here. Just a second. Let me frame a question over here. $400 ml of 0.5 molar B1OH, it is a strong base, plus just a second, plus let me write it as plus 400 ml of 0.5 molar B2OH whole twice. B2OH whole twice. Right? So this is the question. This is the question. We are supposed to calculate the pH of the resulting solution. We are supposed to calculate pH of the resulting solution. You have got 2 strong bases. You are adding the 2 strong bases. You are getting a mixture of 2 strong bases. Get the pH of the final solution. How you are going to do it? How you are going to do it? First of all, This B1OH, just tell me how it would have undergone dissociation. B1 positive plus OH negative, right? This is how it would have undergone dissociation. Similarly, you have got B2 OH whole twice aqueous. How it would have undergone dissociation? It's going to be B2 positive plus 2 times OH negative. This is how these two strong bases would have undergone dissociation. Correct? Now guys, tell me one thing. At time t is equal to 0, can you let me know how many millimoles of B1OH do we have? Can you let me know that? Quickly. Quickly, people. Quickly. Can you let me know how many millimoles of B1OH do we have? See, you know its molarity, you know its volume. Molarity multiplied by volume gives me the millimoles. So we have got 200 millimoles of this particular thing in the beginning. So this has to be 0, this has to be 0. Now this will be 0. 1 mole gives 1 mole. From 200 millimoles, you are going to get 200 millimoles of B positive. 1 mole gives 1 mole. From 200 millimoles, you get 200 millimoles of OH negative. Similarly, how many millimoles of this particular substance we have? How many millimoles of this particular substance we have at time t is equal to 0? Molarity multiplied by volume in ml. So we have got 200 millimoles of B2OH whole twice in the beginning, right? So this will be 0, this will be 0. Now this will be 0. 1 mole gives 1 mole. So from 200 millimoles, you are going to get 200 millimoles. Now 1 mole gives 2 moles. From 200 millimoles, you guys are going to get 400 millimoles, right? Now, if I ask you, how many millimoles of OH negative you are getting from this particular base? 200. How many millimoles of OH negative you are getting from this particular base? 400. If I ask you, how many total millimoles? How many total millimoles of OH negative do we have? Total millimoles. 200 plus 400 makes it 600. So total millimoles of OH negative in the resulting solution is equal to 600. So if I ask you, what about the total net OH negative concentration? Total millimoles of OH negative in the final solution divided by total volume in ml. That's 800. The value is 3 by 4. This is the net OH negative ion concentration. My dear students, if you got the net OH negative concentration, calculate POH. P stands for minus log of net OH negative concentration. The value will be 0.27. Will it come out to be 0.27? Just a second. How much will be the value? We have solved a similar type of question before. The value comes out to be 0.13, sorry. The value will be 0.13, right? The value over here will be 0.13. So this is the POH of the final solution. If you got the POH, calculate pH, which is 14 minus POH. The value will be 13.87. This is the pH of the resulting solution. I hope this is clear to everyone. Yes, is it clear? Is it clear, guys? Quickly. So we talked about pH of the mixture containing two strong acids, pH of the mixture containing two strong bases. Now, what is the third case? Tell me what is the third case? Third case is pH of the mixture containing a strong acid and a strong base. pH of a mixture containing a strong acid and a strong base. Strong acid and a strong base. Let's try to understand. This is slightly different, but it's simple at the same time. For example, I'm writing 100 ml of 0.1 molar H2SO4 aqueous plus 100 ml of 0.1 molar NaOH aqueous. Look at this particular scenario. This is a strong acid. Look at this particular scenario. This is a strong base. Now, you know, when acid reacts with a base, it leads to the formation of salt and water. If you are going to You have got a strong acid on one side, strong base on another side. When you put them in the same container, they'll show a reaction. Acid will react with the base. So basically, when a strong acid is to be treated with a strong base, a reaction will happen. A reaction will happen. So I would say H2SO4 will react with NaOH and it will lead to the formation of Na2SO4, and for example, you are getting water as well. Right? Clear till here? Now tell me whether this particular reaction is balanced or not. This is the reaction which is happening, correct? Tell me whether the reaction is balanced or not. The reaction is not yet balanced. So this has to be 2 times. This has to be 2 times. Now the reaction is balanced, I believe. Right? Now tell me one thing. At time t is equal to 0. Do you know the molarity of this particular solution? Yes, we know it. Do you know its volume? Yes, we know it. So molarity multiplied by volume. It will give me the millimoles of H2SO4 in the first solution. Similarly, how many millimoles of NaOH in the second solution we have? Molarity multiplied by volume. So we have got 10 millimoles of NaOH in the final solution. Correct? Now this will be 0. This will be 0. Now, my dear students, if you remember the mole concept, I had told you whenever you are given with the amounts of all the reactants, at that point of time, you will be using the concept of limiting reagent. Right? Now, the first step for the limiting reagent concept is to balance the reaction. The reaction is already balanced. After balancing the reaction, identify the limiting reagent. How do you identify the limiting reagent? Given millimoles, divide by stoichiometric coefficient. Given millimoles, divide by stoichiometric coefficient. The one which gets the lesser value, that's going to be the limiting reagent. So 10 by 1, that's 10. 10 by 2, that's 5. This one is getting the lesser value, so it has to be the limiting reagent. My dear students, if NaOH is the limiting reagent, that means it would have got completely consumed in the reaction. So I will be left with 0 millimoles of NaOH at the end. When the reaction would have stopped, when the reaction stops at that point of time, there will be 0 millimoles of NaOH in the container. Now, this H2SO4, is it going to be limiting or excess? It's going to be excess reagent. What does that mean? That means out of its 10 millimoles, there will be some millimoles of NaOH left in the container as such. Now, how do we get that? See, I will say, use the stoichiometry. Use the stoichiometry. Can I say 2 moles of NaOH reacts with 1 mole H2SO4. As per stoichiometry, absolutely clear. So 1 mole NaOH reacts with 1 by 2 moles H2SO4. So 10 millimoles of NaOH. 10 millimoles of NaOH will react with 1 by 2 into 10. The value is 5 millimoles of H2SO4. Right? So I got to know with the 10 moles of NaOH, 5 moles of H2SO4 are reacting. With 10 moles of NaOH, with 10 millimoles of NaOH, 5 millimoles of H2SO4 are reacting. How many I had taken? I had taken 10. Out of 10, how many are reacting? 5. So I would say 5 millimoles of H2SO4 will be still left in the container as such at the end of the reaction. Right? 5 millimoles of acid, H2SO4, 5 millimoles of strong acid are still left in the container as such. So tell me, will the resulting solution be acidic or basic in nature? Absolutely, it's going to be acidic. Right? Because in the final solution, we are having a strong acid H2SO4. Now this strong acid H2SO4, which is left in the final solution, how do you think it would have undergone dissociation? It would have undergone dissociation as 2 times H positive aqueous plus SO4 dinegative aqueous. How many millimoles of H2SO4 are left? 5 millimoles of H2SO4 are left. So this will be 0, this will be 0. Now this will be 0. 1 mole gives 2 moles. From 5, you get 10 millimoles. So I got to know the total H positive millimoles which are left in the container at the end of the reaction. So at the end of the reaction, if I ask you, how many millimoles of H positive are left in the container at the end? You'll say 10 millimoles of H positive are left in the container at the end. Right? If 10 millimoles of H positive are left in the container at the end, if I ask you, what is the net H positive concentration? It is total millimoles of H positive left in the container divided by total volume. Total volume is 100 plus 100 makes it 200. So it's 1 by 20. If you got the net H positive ion concentration, can't you calculate pH? pH of the resulting solution, final solution, minus log of net H positive ion concentration, which is minus log of 1 by 20. You just have to solve this term, get the pH of the resulting solution. I hope this is super duper clear to everyone, right? Clear? Is it clear, guys? Quickly. Yes. So all the cases of strong acids, strong bases, I'm damn sure is clear. This is one question which I'm giving you as the homework. Will you be able to solve this question? Just try to understand. Just tell me which kind of question is it? Is it the mixture of two strong acids? Is it the mixture of two strong bases? Is it the mixture of strong acid and strong base? Just tell me that. Just tell me that. Just tell me that quickly. Just tell me that quickly. You just need to identify what kind of mixture this is. Is it the mixture of strong acid, strong base? Is it the mixture of two strong acids, two strong bases? What is it? Once you identify what kind of mixture this is, then only you can use the concept which I gave you. Right? Right, people? So this is your homework question. And let's move on to the calculation of pH of weak acids. Calculation of pH of weak acids, weak bases, and their mixtures. Let's get to know about that. Right? Let's get to know about that. Try to understand one simple thing. Till now, we were talking about only strong acids, strong bases, and their mixtures, right? Now it's time to calculate the pH of weak acids, weak bases, and their mixtures. Let's try to understand. My dear students, for example, you have got a weak acid, HA. This is a weak acid, HA, for example, right? Now this HA, since it's a weak acid, so it will be in equilibrium with its ions. Its ions are H positive aqueous plus A negative aqueous, right? For example, the ionization constant of this weak acid is Ka. Let's assume its degree of ionization is alpha. So what exactly I have done? Try to understand. I have taken a weak acid HA. I'm introducing it into water. When I introduce it into water, it will get dissociated. Now, this acid and its ions, they are going to remain in equilibrium with each other. I'm going to get the pH of the final solution which I got. How do I get the pH of the final solution? In order to get the pH of the final solution, what do I need? I need the total H positive ion concentration in the final solution. Then take its minus log and get the answer. Right? Now, the point is like this. At time t is equal to 0, its concentration is C, this is 0, this is 0. When equilibrium is established in this reaction, it will be C minus C alpha, this will be C alpha, even this is C alpha. Now, dear students, try to write the expression for Ka, which you already know, which is C alpha square divided by 1 minus alpha, right? I am assuming that alpha is less than 0.05. Therefore, 1 minus alpha value, that will be only equal to 1, right? So from there, you can get the value of alpha, under root of Ka by C. This is something which we have discussed in the beginning. Alpha value is equal to under root of Ka by C. Now, if alpha is equal to under root of Ka by C, if I ask you, what about the H positive concentration in the container? You will say it is C alpha. So H positive concentration in the container is C times. Alpha is under root of Ka by C, right? So I would say H positive ion concentration is equal to under root of. Take this C inside. So Ka as such, this is C square divided by C. C got cancelled. So I would say H positive ion concentration here is coming out to be under root of Ka multiplied by C, or you can write Ka multiplied by C whole raised power 1 by 2. This is the H positive concentration in the solution. When you introduced weak acid into water, right? Whatever happened, happened. So the total H positive ion concentration in the container is this much, right? Now, how do we get the pH? P is equal to minus log of H positive concentration, which is KaC raised power 1 by 2. So pH of the solution comes out to be minus log of m raised power n log m. So minus 1 by 2 comes to the front. Then it's going to be log of Ka plus log of C. Correct? So what you need to do is 1 by 2 I'm writing as such, minus log of Ka stands for P of Ka, and it's going to be minus log of C. So this is one direct result. This is one direct result by means of which you can calculate the pH. You can calculate the pH of this acidic solution, which undergoes dissociation under the stoichiometry 1:1:1, right? And I'm assuming this particular formula is valid only when alpha is less than 0.05. And in your NEET, they only ask you these sort of questions. Whose alpha is less than 0.05. They won't give you more than 0.05 case, right? So this is the expression which you have to remember. This is the expression which you have to remember to calculate the pH of weak acids, right? Which undergoes the dissociation 1:1:1. Yeah? Perfect. Is this clear? And do remember, this particular result is only valid when acid's alpha is less than 0.05. I hope this is clear. My dear students, similarly, if you will be having a weak base, for example, pH of a weak base, BOH. When you introduce this weak base into water, it will undergo dissociation. B positive aqueous plus OH negative aqueous. Correct? Let's assume its ionization constant is Kb, degree of dissociation is alpha. Right? Every single thing is same. This is C, this is 0, this is 0. This is C minus C alpha, this is C alpha, this is C alpha. Correct? Now Kb expression, it's similar C alpha square divided by 1 minus alpha. Now assumption, let alpha value is less than 0.05. Therefore, Kb will be equal to C alpha square, or alpha will be equal to under root of Kb by C. If you got the alpha, under root of Kb by C. If you got alpha, under root of Kb by C, we calculate OH negative concentration, which is going to be C times alpha. So C as such, alpha is going to be under root of Kb by C. Finally, it is going to be Kb multiplied by C whole raised power 1 by 2. If you got the OH negative concentration, get the POH of the resulting solution minus log of OH negative net, which is Kb multiplied by C whole raised power 1 by 2. So it's going to be minus 1 by 2 as such. Then it's going to be log of Kb plus log of C. Now use a bit of calculation. You'll say POH is equal to 1 by 2 as such. Minus log of Kb is basically P of Kb, and then it's going to be minus log of C. This particular result is used to calculate pH of a weak base. pH of a weak base whose alpha will be less than 0.05 and which will undergo dissociation under the stoichiometry 1:1:1. I hope this is again super clear to everyone. So quickly let me know in the chats. Yes? Is it clear, people? Quickly in the chats. Is it clear? If it is clear, try to solve these questions. Try to solve this question. Calculate the pH of. It's a weak acid. It's a weak acid. Right? It's a weak acid which undergoes dissociation as CH3COH. How will it undergo dissociation? CH3CO negative plus H positive. How do we get its pH? its pH will be equal to half of P of Ka minus log of C, right? Minus log of C. First of all, you have to calculate, actually you have to calculate first its value, its alpha value. If alpha is less than 0.05, then you'll be using this formula, right? And I'm sure you can calculate alpha. Alpha is equal to under root of Ka by C. Under root of Ka by C. Let me calculate alpha over here first. So alpha is equal to under root of Ka is 1.8 in 10 raised power minus 5 divided by C is 10 raised power minus 1. Root of 1.8 is 1.34 into 10 raised power minus 2. So 0.00134, which is actually less than 0.05, right? So we can use this formula. We can use this formula, right? So now, so pH is equal to half of. Now, let me tell you one thing. In majority, do remember Ka value for acetic acid. Ka for acetic acid is equal to 1.8 into 10 raised power minus 5. And acetic acid is used in majority of the cases. Do remember for once and all, minus a log of 1.8 into 10 raised power minus 5. Do remember its value directly, that is 4.74, always 4.74, right? Now, half of P of Ka, P is minus log of Ka, minus log of this value, that's 4.74, minus log of C, C is the concentration of acid, which is 10 raised power minus 1. So pH has to be equal to half of, it is 4.74 log of m raised power n, which is n log m. So it's 5.74 divided by 2. That's going to be the pH of the resulting solution. That's all. Right? Similarly, this is one more acidic solution. A weak acid basically. First of all, calculate its alpha. Then get to know whether alpha is less than 0.05 or not. If it is less than 0.05, use this particular result and solve the question. And same goes for the last one as well. Yes? Is this concept clear to you quickly? Is this concept clear to everyone? Let's try to solve the second part of the question. Third part you can do on your own. It is 10 raised by minus 3 molar CH3COH. First of all, I'll try to calculate its alpha. Under root of Ka divided by C, which is under root of. Ka is 1.8 into 10 raised by minus 5. C value is 10 raised by minus 3. Root of 1.8 is 1.34. This is 10 raised by minus 1. The value is 0.134. Is 0.134 less than 0.05? No, it's not less than 0.05. Now what to do? How to solve this question? How to solve this question now? How to solve this question now? Do you have any idea of how to do this sort of a question now? In order to solve this question, you have to use the general approach. General approach, my dear student. And what is the see, you won't be using this formula for the second part of the question. You won't be using this formula for the second part of the question. This formula is only valid when alpha is less than 0.05. Here alpha is not less than 0.05, right? So you'll be using the general procedure. And let's try to understand what the general procedure here is. General procedure is very simple. See, CH3COH, when gone into water, it will give CH3CO negative aqueous plus H positive aqueous, right? Its concentration is C, which is 10 raised by minus 3 molar. This is 0, this is 0. Degree of dissolution alpha. So C minus C alpha, this is C alpha, this is C alpha. This is C alpha, correct? Clear till here? Clear till here? Now, write the Ka expression. It's going to be C alpha square divided by 1 minus alpha. Anyways, this sort of a question won't come in your NEET examination, by the way. In NEET, they'll always give less than 0.05 case, right? So K is given, C is given. From here, you can get the alpha. So basically, you'll be getting a quadratic here. You will have to solve the quadratic, get the value of alpha. Yeah? You'll be getting the value of alpha. Once you get the value of alpha, you can get the concentration of H positive. Concentration of H positive in the solution is C alpha. Alpha you'll be calculating from here. C value already you know. So H positive concentration you'll be getting. So pH will come out to be minus log of that H positive concentration. I'm dusted, right? Yeah? Clear? Clear? So basically, it is the concentrations which play here the role. So be careful with all this. Be careful with all these things, my dear students, right? Can you solve this particular question? Calculate the pH of 0.01 molar RNH2 solution. Kb is given. Can you give this equation a try? It's again a simpler one. See, this is water, right? I do not have to consider it. It's in liquid state. Its ectomass is unity. Nothing to do with this. Its concentration of this particular base is C, which is 0.01. So this will be 0. This will be 0. Same procedure. C minus C alpha. This is C alpha. This is C alpha. Or let's not do like this. Let's directly calculate the value of alpha first of all. Alpha is equal to under root of Kb by C, right? Under root of Kb is 2 into 10 raised power minus 6. C value is 10 raised power minus 2. Root of 2 is 1.4 into 10 raised power minus 2. The value is 0.014. It is actually less than 0.05. So whatever neglection we have done, that's absolutely correct, right? So we can use the formula directly. Formula is POH is equal to, what was the formula? 1 by 2 P of Kb minus log of C, right? So POH you can calculate from here, which is half of P of Kb. So minus log of 2 into 10 raised power minus 6 minus what? Minus log of C. C is 10 raised power minus 2. Now a bit of calculation is needed. So 1 by 2. 1 by 2. It's going to be minus log of 2 plus log of 10 raised power minus 6. So it's going to be log of 2. Take minus in between. So it's log of 10 raised power minus 6. And already there is a log of 10 raised power minus 2. Perfect. Now, matter of calculation. So it's going to be 1 by 2 minus times. Log 2 is 0.3. This will be 6. This will be 2. So 6 plus 2 is 8. 8 minus 0.3 is 7.7. 7.7 divided by 2. 7.7 divided by 2. So 3.75 approximately. So this is POH basically, which is 3.75. Since you got POH, now get pH, which is 14 minus POH. So which is 14 minus 3.75. The value is 10.25. This is the pH of the resulting solution. That's all. That's all, right? Simple and basic again. I hope you can solve these sort of questions, right? You should be able to solve. You should be able to solve. Okay, let me just see whether you remember the concepts which we discussed earlier in the today's session or not. Calculate the pH of this particular solution. Let me exactly see whether you remember the concepts or not. 0.1 molar HCl is mixed with 0.1 molar CH3COH. Try to understand. Weak acid, strong acid, one ion in common ion effect. Concentration of common ion is decided by the strong electrolyte. So concentration of common ion will be directly 0.1. So net H positive ion concentration is directly 0.1. So pH of the resulting solution will be directly minus log of 10 raised power minus 1. Value coming out to be 1. So 1 is the pH. No solve, nothing. Don't solve. Right? Use the common ion effect. Weak acid, strong acid, both having one ion in common. And which is the common ion? H positive. So concentration of H positive will be directly equal to the concentration of H positive coming from strong acid, which will be 0.1 only. So net H positive concentration is 0.1. Therefore, pH of the resulting solution will be 1 itself. Right? This sort of equation, you should not need pen and paper now. You should not need pen and paper now. Right? And guys, I think this much is enough for today because my throat is not allowing me to teach furthermore. So, from this particular topic, relative strength of two weak acids. Thursday means day after tomorrow at 6 p.m. We'll have Ionic Equilibrium part 2, in which we shall be discussing the weak acid pH of mixture of weak acids, right? We'll talk about salt hydrolysis, we'll talk about buffer solution, and at the same time solubility product. These are the topics which we shall be discussing on Thursday 6 p.m. right? Perfect. I hope whatever I've taught you today, that's all clear. Yeah. And at the same time, the question which I gave you as the homework, please and please do let me know the answer of that question as well. And do let me know in the comment section whether you understood every single thing or not. But I would want every one of you to join the next session on Thursday, 5 p.m. Right? Sorry, 6 p.m. Thursday. Day after tomorrow, the session is going to be. So day after tomorrow, we are going to finish it. Perfect. So with this, I'll be taking leave. Take care. God bless you all. And see you all on Thursday. Bye-bye.